You must be Dr. Rajat, no?
Yes, I'm Rajat.
Okay. Nice
Hi,
to speak to
nice.
you. Okay. So, how are you? Fine.
Yeah, fine.
ইউটিউব স্ট্রিমিংটা চালু হয়েছে, দেখো তো।
Fine. People are joining now. Okay, we'll talk later.
Yeah. Okay.
হ্যালো। হ্যাঁ, ঠিক আছে। ৰজতদা যদি 100-এর বেছি হৈ যায় তেতিয়া ডিন ছাৰ বিবিন ছাৰো জইন কৰিব নোৱাৰিব। যদি 100 হৈ যায় তেতিয়াহ'লে কিন্তু আকৌ ডিন ছাৰ আৰু বিবিন ছাৰো জইন কৰিব নোৱাৰিব। সেইটো চাব। হ। কি ওই যে জয়েন করেছে। গুড মর্নিং
Sir,
স্যার।
good morning.
Good morning.
So we are just ready to start the session within 10 minutes. 4 minutes is left now, so let's see.
Okay, another 5 minutes or what?
Yes, sir. Within 5 minutes we will start. Go with that. জলদি হ্যাঁ গেলে নহয় গেলে তো কোন শুরু হবে এই সঙ্গে তুমি ইউটিউবটা বন্ধ করে করবে, ঠিক আছে? So,
Good morning, Professor Luis. Myself, Rajat Kantina.
and myself, Dr. Vijay Krishna Devnath from Applied Science Department. Good morning from India. So, shall we start? Time is exactly 9 a.m. Good morning to Professor Firdaus. Oh. Shall we start?
Yeah, you can, Professor.
Okay. So, good morning to one and all present over here. So, we are pleased to welcoming you all. I, Dr. Vijay Krishna Devnath, on behalf of this organizing committee, humbly welcoming you all to this 2 days international conference on emerging trends in pure and applied mathematics at Tezpur University from March 12 to March 13 in blended mode. So, for your kind information, we are happy to inform you that in this international conference, more than 400 research scholars and faculties registered for the conference, and also we received registration of participants from the countries like Philippines, Pakistan, Nigeria, Indonesia, Algeria, Palestine, etc. So also we receive papers in the field of group theory, ring theory, fluid dynamics, computational fluid dynamics, game theory, number theory, graph theory, operation research, etc. And very renowned professors from worldwide give their keynote speaker in the plenary and invited talk session. So this conference is basically intends to bring researchers, scientists, academicians, and research scholars together to exchange their knowledge and experience, new ideas, and the research outcomes of all possible aspects of pure and applied mathematics. So this Department of Applied Science is one of the newest department of this university. Was established in the year 2019, and our collaboration department, that is the Department of Mathematical Science, is one of those oldest department at the time of build this university, that is in 1994. So today we have with us our Honorable Pro Vice Chancellor Professor Dhruva Kumar Bhattacharya, and our Honorable Dean School of Engineering Professor Parthopratim Sahu sir. So I welcome both of you, sir. Also, I welcome some distinguished keynote speakers like Professor Mark Lewis and others to these inaugural sessions. Welcome, sir. And also at the last, I welcome to all these participants who are in the Google Meet and who are in the YouTube session. So I welcome you all. Now, two of our students will sing Saraswati Mandana and a Saraswati Bhajan. So I request them to play these songs.
या कुंदेरु तुषार हार धवला या शुभ्र वस्त्रावृता या वीणा कर दंड मंडित करा या श्वेत पद्मासना या ब्रह्माच्युत शंकर प्रभृतिभिः देवै सदा वन्दिता सा मा पातु सरस्वती भगवती निःशेषजाड्यापहा
वीणावादिनी ज्ञान की देवी अपनी दया बरसा देना मेरे सिर पे हाथ धरो माँ ज्ञान की ज्योति जगा देना ज्ञान की ज्योति जगा देना ज्ञान की देवी अपनी दया बरसा देना मेरे सिर पे हाथ रखो ज्ञान की ज्योति जगा देना ज्ञान की ज्योति जगा देना तू सारे संगीत सारे रागों में आभास तेरा रागों में आभास तेरा साजों की आवाज तुझी से सारे सुरों में वास तेरा सारे सुरों में वास तेरा सारे सुरों में वास तेरा राग रागिनी मेरी सरगम इनको और खिला देना मेरे सिर पे हाथ धरो माँ ज्ञान की ज्योति जगा देना ज्ञान की ज्योति जगा देना वादिनी ज्ञान की देवी अपनी दया बरसा देना मेरे सिर पे हाथ धरो माँ ज्ञान की ज्योति जगा देना ज्ञान की ज्योति जगा देना थैंक यू
So it was a very pleasure to hear from both of you. Thank you once again for being with us. Thank you, both of you. Now I request our Honorable Vertices sir to address the gathering. Please, sir.
Thank you, Dr. Vijay Krishna. Esteemed distinguished speaker, Professor Lewis, and other distinguished speakers from abroad, all those invited speakers from India, my dear colleagues, learned participants of the conference, and all the members of the organizing committee. I'm indeed very happy to be a part of this inaugural session. This is perhaps the first international event organized by Department of Applied Science in association of Department of Mathematics of Tezpur University. So I believe that this will be a grand success. Already Dr. Vijay Krishna has mentioned that almost 400 faculties and researchers from various countries like Philippines, Pakistan, Nigeria, Indonesia, Algeria, and Palestine have joined in this conference. So definitely this will be a very fruitful platform for all the participants to have discussion on the various mathematical subjects. There is a galaxy of invited speakers I have seen who will be delivering their speech on various topics, which already Dr. Vijay Krishna has mentioned. And I believe that there will be interaction after the speech, and it will definitely give a very good platform to all the young and budding researchers to find their research problems and to carry out their research in various fields of mathematical science. Conferences always help improve visibility of a department of an institution in a country or in a globe. So this conference also will help definitely to bring more visibility of both the Department of Applied Science and Department of Mathematics globally. And after the conference, I believe that there will be future collaboration There'll be feature interaction with the researcher across the globe, and it will open up many new research problems to carry out for the young researchers in future. So Tezpur University always has been encouraging such national, international event to organize. And this will be definitely, I believe that although in blended mode, the people will take the advantage because if the bandwidth is okay, if the network connectivity is fine, then you will not feel whether it is a online talk or whether it is an offline talk. So the talk material when will be shared, I believe that everybody can take advantage out of this. And I feel that since in the recent times, ministries, funding agencies, they have opened up different schemes, but they expect more and more multidisciplinary nature. So the people, researchers in mathematics department, I believe will collaborate with the other disciplines and they will take the advantage out of this. India is trying to implement NEP 2020 in a big way. Every higher educational institutions and great emphasis for all of us implement it. And one of the major focus of this policy is to implement multidisciplinary research. So we have established one Center for Multidisciplinary Research to enable or to encourage, to motivate the researchers from across the discipline to take the advantage out of this and can take up a real life problem and solve it for the mass people. There are many problems where without mathematics is not at all possible. I am doing research in machine learning, and I know that mathematics has very important role, crucial role there. So, but we need some form of collaboration. We need some form of multidisciplinary approach so that people can take up problems in any domain and can apply his or her expertise in solving the problem. The talk material, whatever will be presented here, I believe it will be recorded, that will be shared, disseminated, so that those who are attending, they can take the advantage out of this, and those who could not attend, they also can take the advantage later on also. Because such a gathering, resource persons always may not be possible. So we should take the advantage out of this. And if possible, the content of those talk can be in the form of a proceedings by reputed publishers. You can publish it so that everybody can take advantage out of this. So thank you very much for giving me this opportunity to be a part of this inaugural session. And I believe that people will definitely take this advantage, and next 2 hours there will be definitely out of this both 2-day session. There will be good interactions, and apart from this talk delivery and whatever the questions are there, and they will raise and they will take the advantage of this resource persons. Also, I expect at the day end, there will be some research questions which later on our researcher can take up, and some collaboration activity or collaborative activity will go on in future. With this, I conclude my speech. Okay. On behalf of Tezpur University as a Pro Vice Chancellor, I invite you to this conference, and please enjoy this conference with full of his effort. Thank you very much.
Thank you, sir, for your kind words. I believe that these words can be uh, em- applied to our mathematics domain. And I should inform the audience that sir is a renowned professor in the field of machine learning, network security, and bioinformatics. Thank you once again, sir. Now we have with us our Dean Sir, Dean School of Engineering, Professor Parthopratim Sahu Sir, who is a specialist in optics network, integrated optic device, split spectrum technology for wireless communication, neuroengineering, etc. So I welcome Professor Shao sir to deliver his address. Over to you, sir.
Thank you, Vijay Krishnath. At the outset, I'd like to congratulate Vijay Nath as well as the Applied Science Department, Mathematics Department for wonderful conference. Esteemed researchers and faculty member of this university and my dear participants, ladies and gentlemen, and honorable Vice Chancellor, Professor D.K. Bhattacharya and Professor Luis. I'm seeing the display.
Hello.
It is my great pleasure privilege to give a speech on inaugural session of this conference, and I'm happy that 400 participants will be joining to this conference, and from different countries such as Algeria, Palestine, Pakistan, Sri Lanka, Philippines, Nigeria, also USA. I hope that young participants, researchers, students will enhance their knowledge through interaction. Although it is a blended mode, through interaction, online interaction, they can enjoy the conference. As you know, engineering and science without mathematics cannot go. So always mathematics should be there. Not only in engineering and science, also humanities, biological science, medical science. There are a lot of application of mathematics in computation biology, such as disease modeling, neuromodeling, nervous system modeling. So in fact, we are working on neuromodeling using mathematical tools with transmission lines models in our laboratory. And we cannot think about the mathematics, especially in the economics, finance management. Mathematics is a part of that also. So this is an important event, but as well as this participants or other participants, that you will be interacting each other through this conference, and will enjoy the conference. So coming back to Tezpur or Tezpur University, those who are outside, especially for them, Tezpur is one of the oldest city in India. It's around more than 3,000-year-old city, and there are a lot of events, lot of happenings are there in old days, and you can see everything in the outline. And it's one of the cleanest city in the world. So I request the participant, both abroad and India, to come to Tezpur to see. And to our university have 28 department, really. And the Applied Science Department is one of the young department, and Mathematics Department is one of the oldest department. So both these two departments combined together to organize this conference. I'm happy to know that. And as far as the research is concerned in the world, I'd like to tell a few things. As Professor D.K. Bhattacharya has told, that multidisciplinary approach is very, very important to any type of, not a single discipline can do the research now. So all the innovation will come through only multidisciplinary approach. Not a single discipline can do. So this is the platform. These are the platform we can use the interdisciplinary type of thing. Not only mathematics people, other peoples also can be interacted through this media. In fact, I'll be attending most of the. I've seen the schedule. I'll be listening many lectures. I've seen it is of my interest. And at last, I congratulate Applied Science Department and Mathematics Department to organize this. I hope that this conference will be successful one. Thank you very much.
Thank you, sir, for your kind words. We believe that under your guidance, we definitely can do some more collaborative work inside the university and outside the university. So, thank you once again to our Honorable Pro Vice Chancellor, sir, and our Honorable Dean, sir, to deliver their kind address. Now, I would like to invite Dr. Rajat Kanti Nath to give a vote of thanks to this inauguration session, and followed by our keynote speaker talk by the Professor Mark Lewis at 9:30 o'clock. So I just hand over to Dr. Rajat Kanti Nath to give the vote of thanks. Over to you, sir.
Thank you, Vijay. I would like to thank our university to give this opportunity to organize such a nice international conference. My thanks to our Pro Vice Chancellor, Sir, Professor Bhattacharya, and Dean Sir, Professor Shahu. They help us to organize this conference. Then I must thank all the speakers. In our very short notice, they have agreed to give their deliberations. I thank Professor Lewis, Professor Nita Shah, Professor Ashok Kumar Vuniya, Professor Ritumani Sharma, Professor Indranil Ghosh, Professor Devajani Chakraborty, Professor Manoj Kumar Yadav, and Professor Irfanian. These are the speakers of this talk. And to organize this talk, I must thank all my colleagues from the Department of Mathematical Sciences and Department of Applied Sciences. All of them have nicely helped us to formulate this workshop. I must thank all the participants. Yes, Vijay Krishna and Pro Vice Chancellor already mentioned that we have participants from across the globe. We are happy to say that we have participants from UK, from USA also. And my research scholars also, our department research scholar and research scholar from Applied Sciences, they help a lot. They work together with us to bring this conference. And finally, I would like to thank all the participants. I'm sure the participants will definitely get benefited from this conference. Thank you. Thank you all. Our next session, inaugural session, will be started at 9:30. So I think it's better we should wait for some minutes so that we can get more participants. Thank you.
Thank you all. Here it concludes the inauguration session. ক্লাস এটা তো সবাই ইউটিউবে দেখতেছে বেশি নাই
Good morning, Manoj sir.
Sorry, Rajat, I was muted. Good morning. How
Good
are you?
morning, sir. Good morning. I'm fine, sir. So just now we have finished our inaugural session, and
Okay, great.
I'm just waiting for 5 minutes to start the first talk.
Yeah.
Professor Luis already joined in
Yeah,
this
great.
meeting.
Yeah, I was just filling my water bottle or my glass of water in case I need a drink.
Hi, Luis.
Hello.
Hi, sir.
Sorry, it would be morning. It's what 9:30 there.
Yes.
Yes, sir. It is almost 9:30 here, and
Yeah,
probably there it is midnight.
11 p.m. Yes.
Sorry.
So I'll finish at midnight, or you will be asking questions at midnight. So.
Professor Luis, what is the weather condition in US? Weather is good now? It's too cold.
We're getting some snow tonight. It had warmed up and we had melted off most of the snow, and we'd had some warm days, and then today, most of the day was rainy, and then this evening it turned into snow, and we've got, I don't know, at least the ground is white outside, so we probably got a 1/4 inch of snow outside. I think it's supposed to snow overnight, and then tomorrow be cold, and then warm up again. And it's late enough in the year we won't have snow very long now, but yeah, we're getting another blast of winter yet.
My friend,
I don't think you would. Go ahead.
My friend 1 week before he called me from the Virginia Tech. He said there is a snowfall, heavy snowfall in Virginia Tech 1 week before.
Yeah, there was a storm yesterday, so probably that's an effect of that.
Okay.
We had a couple of big snowfalls in January or February this year, and then mostly it's just been cold. But I mean, the last week it's been several warm days. It felt like actually spring was getting started. So we had days where, it was there were a couple days which felt more like May than March. So. But we can have snow. We've had snow in April. In fact, I think we've even had snow in May once or twice. So, I knew it was too soon, that we weren't going to get away with not having more snow yet.
Dr. Nath.
Yes, sir.
Now 9:30.
Yeah, sir. We are going to start. Once again, I welcome you all to the first plenary session of this conference. I am very happy to say that Professor Luis is with us and he will deliver the first plenary talk today. Professor Lewis earned his PhD at the University of Wisconsin-Madison in 1995 under the direction of Professor Martin Isaacs. He joined the faculty at Kent State University in 1996 and have been there since then. He has expertise in the area of group theory, graph theory, and character theory of finite groups. Professor Lewis has published more than 150 papers and he has more than 900 citations. He has produced 10 PhD students, and he is also serving as editorial board member of our very reputed journals like Communications in Algebra, Journal of Algebra and its Applications, International Journal of Group Theory, etc. Today, he will discuss about groups. He will discuss about graphs on groups. In particular, he will talk about commuting graph and several related graphs. We are very happy to listen from him. Professor Lewis, please.
All right, thank you. I'd like to thank you. Thank you for the invitation and thank you for having me. Let me share my my screen here. Okay. No, actually, here. All right. All right. There. Okay. So this is a talk I've given a few times before, so you may have seen it. If you have, I apologize. Also, I know that Peter Cameron has been giving a talk with a similar title that's also about generalizations of the commuting graph. I've seen the talk. I've seen his recording of his talk and looked at his paper. And interestingly, there's actually not that much overlap between what he's been talking about and what I'm talking about. There seems to be a real explosion of graphs, the interaction of graphs and groups, and so there seems to be a lot to talk about in this topic. So, and a lot going on, and I think there's a lot more to be studied. Throughout this talk, all groups are going to be finite. All graphs are simple. That means that, I'm only allowing at most one edge between two vertices, and any edge has to be between two distinct vertices. I'm not allowing any loops. So recall that a graph is a collection of vertices and edges between vertices. And as I said, I don't allow multiple edges or loops. Okay. There are a number of different graphs that can be associated with groups. The most well-known graph associated with groups is the Cayley graph. I'm not going to talk about that one. Another one that's been associated with groups is the graph that's often, or what used to be called the prime graph, but these days is mostly called the Gruenberg-Kegel graph. And the prime graph actually has been applied to a whole bunch of different graphs with groups. And so to be consistent, I think the Gruenberg-Kegel graph is a better name. Technically, I'm not talking about that graph either, although that graph actually comes up in the background. And I mean, there's certain of the results that we use for which knowing the Gruenberg-Kegel graph is useful. So the Gruenberg-Kegel graph is in the background, but I'm not going to be talking about it explicitly here. I'm going to talk about several related graphs. So one means of associating a graph to a group is the following. Pick a class of groups. I'm going to call it C. For the set of vertices, I'm going to fix a subset omega of G. If X and Y are in omega are distinct elements, we put an edge between them if the subgroup that X and Y generates lies in C. And we're going to consider in the talk, we're going to consider three possible classes for C. The classes we focus on are abelian groups, cyclic groups, and solvable groups. In the literature, nilpotent groups have also been considered. And in fact, I think nilpotent groups are probably the next area where there's probably going to be a lot of interest. But there really only one real paper that really have looked at nilpotent groups so far. So there's not as much that's been said so far about that. But I think there's a lot more that should be said. And you can obtain a complement to such a graph by taking the same set of vertices, putting an edge between x and y exactly if x and y is not in C. And in some sense, this class of graphs was motivated by the commuting graph. So let's start with talking about the commuting graph. The commuting graph of G is the graph with a vertex set G minus the center of G. And there's an edge between x and y if x and y commute. Right, so that is if x times y equals y times x. And that's equivalent to saying that that the subgroup generated by x and y is abelian. So hence the commuting graph arises when we use the class of abelian groups. And the commuting graphs were first studied by Brouwer and Fowler in 1955 in relation to the classification of the non-abelian simple groups. They were really first studied in their own right by Segev and Seitz in terms of the classical simple groups. And in fact, much of the research regarding the commuting graph is related to simple groups. I mean, certainly the early research is all related to simple groups. Lately, there's been a lot more results about commuting graphs on other groups. And I'm not going to try to describe all this research, but it really culminated in a paper by Solomon and Woldar, where they proved that if S is a non-abelian simple group and G is any group, and S and G have isomorphic commuting graphs, then S and G are isomorphic. So basically, the commuting graphs, at least in the simple groups, are capturing all the information about the groups. At the opposite end of the spectrum from non-abelian simple groups are solvable groups. Non-abelian simple groups have no normal subgroups. As my advisor, Marty Isaacs, like to say, solvable groups are groups with lots of normal subgroups. So they're sort of at the opposite end of the spectrum. And in a seminal paper, Parker shows that if G is a solvable group with a trivial center, then the commuting graph of G is disconnected if and only if G is a Frobenius group or a two-Frobenius group. And I should say group G is a two-Frobenius group if there exist normal subgroups K and L, so that G mod K and L are Frobenius groups, and the Frobenius kernels are L mod K and K respectively. So they're two Frobenius groups in the sense that the group is made out of two different Frobenius groups, which are sandwiched on top of each other in a particular way that works well together. Parker also proved that the commuting graph of G, still under the assumption that the center is trivial and G is solvable, is connected, then the diameter of the graph is at most 8. And he provides an example of such a group whose graph has this diameter. Furthermore, in a separate paper, Morgan and Parker removed the solvable hypothesis, and they proved that if G is any group where the center is trivial, then the connected components of the commuting graph all have diameters at most 10. I don't believe they actually have any examples. I don't know that it's known that were there any examples where 10 is actually met, but they proved that 10 is the bound. Now, if you remove the hypothesis that the center is 1, the situation is much less clear and pretty wide open. There's not that much known. On the other hand, it is known that there is no bound in the diameter of the commuting graph of solvable groups with non-trivial centers. In particular, Guiducci and Parker have presented a family of two groups which have no bound on the diameter of the commuting graphs. In particular, they present a family of two groups, and which you tell me you give a diameter, and there's some two group in that family whose commuting graph has diameter larger than the diameter you've given. So you can't bound. There is no universal bound on the diameter commuting graphs. Okay, so an RU is a research experience for undergraduates. This is something that the National Science Foundation here in the United States supports. These are programs that the university puts on, universities across the United States put on in the summer, where they bring small groups of undergraduates to universities to work together in a research experience with professors. And so at Kent State, we had an RU that was ongoing, and in 2019 and 2020, I supervised RUs. And so in the summer of 2020, the RU I was supervising looked at the situation, and the students in the RU were Nicholas Bikey, Colin Heath, Kaiween Liu, and Jamie Pierce. And the graduate students I had working with us were Rachel Carlton and David Costanzo. And we were able to generalize the results of Parker and Morgan and Parker. And particularly, we were able to prove the following. And I'm going to use gamma of G to denote the commuting graph of G. And so we were able to prove, so let G be a group and let Z be the center of G. And suppose now that the derived subgroup of G intersected with Z is 1, then we were able to prove that the commuting graph is connected if and only if the commuting graph of G mod G is connected. We were proved that every connected component of the commuting graph has diameter at most 10. We proved that if G is solvable and that the commuting graph is connected, then the commuting graph has diameter at most 8. And if G is solvable, then it's disconnected if and only if G mod the center is either a Frobenius group or a 2 Frobenius group. So in particular, we were able to replace Parker or Guiducci and Parker's hypothesis of the center being equal to 1 with just requiring the G prime intersected with the center being equal to 1. So that was a nice result, and it was happy that we were able to do that. And in particular, if you think about an A group, so an A group is a group where all the CELO subgroups are abelian, and it's known that if G is an A group, then G prime intersected with the center is equal to 1. So this theorem 1 applies to A groups. So in particular, A groups have the property, if you have a solvable A group, and the graph is connected, the commuting graph is connected, then its diameter is most 8. Then my PhD student, Rachel Carlton, has been working to improve the diameter result for solvable A groups. And at this point, she can prove that if G is a solvable A group and gamma of G is connected, then the diameter of gamma of G is at most 7. And in fact, this week, she actually just finished proving that the diameter is at most 6. This weekend, I believe, just working on verifying that her proof is correct. There's still a gap though, because at this point, the largest diameter that we know of a solvable A group is 5. So there's still a question of, you know, is 6 the right bound? Is there some solvable A group where the commuting graph has diameter 6, or can she still improve or bound one more? You know, but I mean, you know, she's been able to do quite well by knocking 2 off from the 8. So that we're making progress there. Yeah, I should also mention that the hypothesis that G prime equal to or G prime intersecting the center being 1 can be weakened even further. If I look at just the set of commutators rather than the subgroup generated by the commutators, the hypothesis I really need is that the set of commutators intersected with the center is equal to 1. And using gap, we have found groups where the set of commutators intersected with the center is 1, has size 1, but G prime intersecting the center is non-trivial. One further result that we proved along these lines is that if we have a group G where G mod the center is either a Frobenius group or a 2 Frobenius group, then in fact the commuting graph is disconnected. We don't need even solvability there to get that. Okay. So then I want to now shift gears a bit and talk about one generalization or one generalization of the commuting graph, and that's a cyclic graph. And so for this graph, the vertex set is going to be the set of G minus the identity. And we're going to put an edge between X and Y now with the subgroup generated by X and Y is cyclic. In the literature, a graph that's been studied a lot in the literature is the power graph. And the power graph is the graph whose vertex set is G. And there's an edge between X and Y if X is a power of Y or Y is a power of X. The punctured power graph, you throw away the identity and take the same edges. It's not difficult to see, or take the graph that you get by taking the edges on the subset of vertices. Not difficult to see that the punctured power graph is a subgraph of the cyclic graph. And we note that the graph with G as its vertex set and edges between X and Y is cyclic, has sometimes been called the enhanced power graph in the literature. And then the punctured enhanced power graph has been used in the literature, and that's really just another name for the cyclic graph. And it's easy to see that the cyclic graph is a complete graph if and only if the group G is a cyclic group. And a number of years ago, I and Diana Apertori showed that if all the connected components of this graph are complete graphs, if and only if the group is partitioned by cyclic subgroups. And then, as I said, I supervised an RAU in 2020. I'd also supervised an RAUs in 2019. And the 2019 RAU I supervised considered cyclic graphs. And the students of the 2019 RAU were Stefano Schmidt, Eob Tesgay, and Gabe Udall. And the graduate student who worked with me that year was David Costanzo. And it's easy to see that if G is a P group for a prime P, the cyclic graph is connected if and only if G is cyclic or generalized quaternion. And in fact, if G is a P group for some prime P, the number of connected component just equals the number of subgroups of order P. You can do a find a bijection between the connected components and the subgroups of order P in the group. So I'm going to use delta of G to denote the cyclic graph of G. If G is nilpotent but not a P group, you can prove that if the order of G is divisible by at least 2 primes, then the cyclic graph is connected and the diameter of the cyclic graph is at most 3. And in fact, we can determine exactly which nilpotent groups have diameter 2 and which have diameter 3. So if you take G to be a nilpotent group that does not have prime power order, the following are true if at least one but not all the CELO subgroups are cyclic or like generalized quaternion, then the diameter is 2. If no CELO subgroup is cyclic or generalized quaternion, then the graph has diameter 3. And one key point about nilpotent groups that are not P groups is that they're non-trivial direct products. And that's what the 2019 RU, one of the things that they really started looking at were cyclic graphs of non-trivial direct products. And they were able to bound the diameter of the direct products when the factors have coprime orders. In particular, they were able to show that if G and H were non-trivial groups with coprime orders, then in fact the cyclic graph is connected and its diameter was all less than or equal to 3. So they really were getting the same result as in the nilpotent case, but here we're not assuming that G or H are nilpotent. We're just assuming that they have coprime orders. In general, we were able to prove that if G and H were non-trivial groups, and we just assumed that the graph is connected, then we were able to prove that that the graph of the direct product has to be at most 7. And we were able to get an example of a graph whose diameter was 7. You take G to be this small group from the GAPS small group library, and H to be the Frobenius group of C4 acting on 2 copies of the cyclic group of order 9, and the resulting group has diameter 7. Now, if you take G to be a non-cyclic P group and H to be a non-cyclic Q group for distinct primes P and Q, we know that the graphs of G and H are going to be disconnected. On the other hand, lemma 6 says the graph of the direct product will be connected and the diameter is at most 3. So the connectedness of G and A of the direct product in general does not imply the connectedness of the graphs of G or the graph of H. But when the graph of GH has diameter that's very sufficiently small, we're able to get information about the cyclic graphs of G and H. So in particular, if G and H are groups and the diameter of the direct product is less than or equal to 2, then either the diameter of the graph of G had to be less than or equal to 2, or the diameter of the graph of H had to be less than or equal to 2. So, I mean, in a very small case, we're able to get something about diameter, but that's really the only case. In general, we're really not able to get, usually not able to get information about the graphs of the component from the graph of the direct product. Now, we have determined exactly when the cyclic graph of a non-trivial direct product is disconnected. And the condition we need is a condition that we called C1 of P. And this condition says there exists an element in G of prime order P whose centralizer is a P group. And so let G and H be non-trivial groups, then the graph of G cross H will be disconnected exactly, or if and only if GA cross H satisfies C1 sub P for some prime P. And as a corollary, if G and H are non-trivial groups, then the graph of G cross H is disconnected if and only if there exists a prime P such that G and H each satisfy C1 of P for the same prime P. Okay, and now we'll look at another topic studied by the 2019 REU. And that's a Z group. And so a Z group is a group where all the CELO subgroups are cyclic. Not surprisingly, these groups have a very restricted structure. What they were able to show, or what we were able to show, is that if G is a Z group, then the cyclic graph is disconnected if and only if G is a Frobenius group. Also, we were able to show that if G is a Z group, and the graph is connected, then the diameter is at most 4. And if G is a Z group, then the diameter is at most 2, exactly when the center is not 1. So if the center is 1, the diameter is 3 or 4. If the center is not 1, the diameter will be 1 or 2, or 2 in particular, unless the group is cyclic. And we could provide examples of Z groups with diameters 2, 3, and 4. And then finally, with that group, we consider the cyclic graphs for PQ groups. So we let PQ be distinct primes and let G be a PQ group. Then the diameter of the graph is 2, if and only if G has a unique subgroup order P or a unique subgroup order Q, and that subgroup is central in G. For PQR groups, the result that we get is not nearly as strong. If we were able to show that if G is a PQR group and the cyclic graph has diameter 2, all we were able to show, what they were able to prove is that the center is bigger or equal to 1. We were trying to get a result like Theorem 14 that there had to be a unique subgroup of some particular prime order, but we weren't able to do that. The best we were able to do was to get that the center had to be non-trivial in that case. Notice next. So next, I'm going to talk about Frobenius groups and 2 Frobenius groups. Now, if G is a Frobenius group or 2 Frobenius group, then the center is 1. And it follows in that case that the cyclic graph and the commuting graph are the same set of vertices. And so if you think about it, that means that the cyclic graph of G is going to be a spanning subgraph of the commuting graph of G. That means that they have the same vertices. And every edge in the cyclic graph is an edge in the commuting graph. And we know from Parker's result that the commuting graph is disconnected when G is a Frobenius or 2 Frobenius group. And so it follows that the cyclic graph is also disconnected for either of these groups. Now, when G is a Frobenius group with Frobenius kernel N, it's not difficult to see that the number of connected components in the commuting graph of G is 1 plus the size of N. And when G is a 2 Frobenius group, where K and L, again, satisfy this condition, that G and G mod K are Frobenius groups, that L and G mod K are Frobenius groups with kernels K and L mod K, then the commuting graph of G has 1 plus order of K connected components. Now, counting the number of connected components of the cyclic graphs is more complicated, And the following is work that David Costanzo, and some of this work ended up in David's PhD dissertation. And we're going to set M sub P of G to be the number of subgroups of order P in G. And for Frobenius groups, we obtained the following. So let G be a Frobenius group with Frobenius kernel N. If N is a P group for some prime number P, then the cyclic graph has order N plus M sub P of N connected components. If N is not a group of prime power order, then the cyclic graph has order N plus 1 connected component. So the number of connected components there depended on whether N was a P group or did not have prime power order. For two Frobenius groups, turned out to be a much more complicated problem. So first we have the formula for when K does not have prime power order. So let G be a two Frobenius group where K is as in the definition. If the order of K is divisible by at least two distinct prime numbers, then the cyclic graph has the order of K plus 1 connected components. Notice that was the same as the cyclic graph. Next, we find that the formula when K and G mod L are P groups for some prime P. And here, so we let G be a two Frobenius group. We assume K and G mod L are P groups for the some prime P. Then the number of connected components in the cyclic graph is order of K plus M sub P of G. This is again similar to the Frobenius group case, but more than what we were getting in the commuting graph case. Finally, the case when K is a P group and G mod L is not a P group for some prime P, and this is the really most complicated case. So we take G is a two Frobenius group, P is a prime number, K is a P group, G mod L is not a P group. Then the number of connected components is the order K plus the index of L and K plus this number M sub P star, where M sub P star is the number of subgroups of order P and G that are not centralized by an element of prime order other than P, of order other than P. And I mean, you know, I'm not a formula I'm thrilled with, but what we got, so it's what it is. And so, you know, you have to take what, I mean, and in the groups we were actually computed it, and this is the number that works. So, you know, and this is what we were able to prove. So you live with what you get. Okay, I'm going to switch gears again. If gamma is a graph, we say that V is a universal vertex. If V is adjacent to all the other vertices in gamma. To understand the connectivity of a graph, it's often useful to find the universal vertices and throw them out. And sometimes when people talk about the commuting graph, they take the set of G to be, the set of vertices to be G or G minus 1. Taking the edges as in the commuting graph, X is a universal vertex if and only if X is in the center. It's not hard to see that the universal vertices in that graph would be exactly the elements in the center, which is why we were taking the set of vertices to be G minus the center. In the cyclic graph, if one were included, it would be a universal vertex, which is why we were omitting it. In fact, one is not necessarily the only universal vertex, and this has been an open question regarding the description of the universal vertices of this graph. And based on the work in the 2019 RAU, we can describe the set of universal vertices for this graph. So let G be a group take an element little g and g, and let pi be the set of primes dividing the order of little g. And then we're going to write g as a product of the g sub p's, where g has p power order for each of the primes in pi, and g sub p and g sub q commute for all the elements p prime for the primes p and q and pi. It's well known that you can do this, that you can always take your element of the group and decompose it into its prime parts. And in fact, this can be done uniquely. Then G is a universal vertex if and only if for each prime in pi, the CeLO P subgroup of P and G is either cyclic or generalized quaternion, and this element G sub P is contained in P intersected with the center of G. So, that tells us exactly when we have a universal vertex. Okay. Now, one can show that the set of universal vertices in a cyclic graph is a subgroup. This was actually done in a paper by O'Brien, Patrick, Cyclic, and Wepsick. And it maybe makes sense then to re-examine the results in the literature looking at the non-universal vertices for the set of vertices for the graph on the set of non-universal vertices. So I think that may be worth thinking at. Now, in the spirit of O'Brien, Patrick, and Smithline and Wepsick, I want to look at a result or look at work that they first looked at. And so I'm going to define the set given a G element or group G and an element X. I'm going to define the set SIC of X, which are the set of elements Y and G, sets of the subgroup generated by X and Y in cyclic. Notice that this is the set of neighbors of X in the cyclic graph. It's not difficult to see that this set is usually not a subgroup of G. I should mention in the commuting graph, the set of neighbors of X is the set of elements that centralize X. That is the centralizer of X, which is a subgroup of G. So in some sense, the cyclic graph and the commuting graph have behaved differently, because in the one graph, the set of neighbors is a subgroup. In the other graph, the set of neighbors is not a subgroup. But it makes sense to study groups where this is a subgroup for all X and G, and in the literature, these groups are called tidy groups. An abelian group is tidy if and only if each of its CeLO subgroups is cyclic or elementary abelian. These guys that I mentioned before proved that in their paper. My 2020 RIU studied tidy groups. When we were able to prove several things. In particular, when G is a P group, we studied that where we showed that a P group is tidy if and only if it has exponent P, it's cyclic, or P is 2 and it's dihedral or generalized quaternion. Note that a nilpotent group is tidy if and only if its CeLO subgroups are tidy. Again, that was proved by that quartet. So basically then using the results on P groups, you could determine exactly which nilpotent groups are tidy. We're able to get strong information about tidy solvable groups. Note that subgroups of tidy groups are tidy. So the CeLO subgroups of tidy groups are all tidy. But we have examples that show that the converse is not true for solvable groups. There's solvable groups which are not tidy, but the CeLO subgroups are tidy. However, if we look at the Hall subgroup for sets of 2 primes, we do have a converse. So suppose G is a solvable group and let pi be the set of prime dividing the order of G. If G has a tidy Hall row subgroup for each subset row contained in pi of size 2, then G is tidy. Furthermore, we can classify the tidy PQ groups. This is what they end up being, is here and here. I don't want to read all that off. You can see, read a reasonably complicated description, but that's what we are able to do that. I note that the definition of tidy groups is not compatible with particularly compatible quotients. It's been noted by these 2 gentlemen that quotients of infinite tidy groups are not necessarily tidy, but we are able to prove that quotients of finite solvable tidy groups are tidy. So if G is a finite solvable tidy group and N is a normal subgroup of G, then G mod N is tidy. We are also able to use this to bound the fitting height of tidy solvable groups. So if G is a solvable tidy group, then G has fitting height at most 4, and G mod the fitting subgroup has derived length at most 4. And in fact, if the order of G is odd, then the fitting height is at most 3, and G mod the fitting subgroup is abelian or metabelian. So in particular, what we're able to say is that the solvable tidy groups are very much restricted. Next, I want to talk about the solvable graph. This is the third of the graph that I mentioned before. So this is the group. This is the graph where the edges occur, where x and y is solvable for x and g. We write S and G for the solvable radical of G. This is the largest normal subgroup of G that is solvable. A theorem of Thomson states that if G is a group and X is in G, then the subgroup X and Y is solvable for all Y and G if and only if X is in the solvable radical. So the universal vertices of this graph are precisely the elements of the solvable radical. And so a corollary is that this graph is complete exactly when G is solvable. So if a group is G, we define the solvable graph to be the graph G minus the solvable radical, and there's an edge between X and Y whenever X and Y is solvable. And in a paper with these 2 gentlemen, we considered these graphs, and we were able to prove that this graph is connected and the diameter was at most 11. However, a more recent paper by these three authors has been posted on the archive, and they are actually able to improve our bound, and they prove that the diameter is actually at most 5, and they give examples where the diameter is 4. So they're able to get much closer, much better bound than we're able to get. Pardon me. If we look at this graph, the neighbors of this graph are the set of y's such that the subgroup generated by x and y is solvable. Again, it's not difficult to see that this is not necessarily a subgroup. And in fact, but in A5, the set is a subgroup when x is order 5, not a subgroup otherwise. We proved that the group G is solvable if this set is a subgroup for all elements in G. And we also prove that if there's just one element, this I found, this was proved by my co-authors, and when they said this was true, I didn't believe them, and I said, prove it, and they wrote down a proof, and yeah, so I'm actually rather amazed. To So you take one element, you just need the elements of this set to commute pairwise. We're not even assuming this set is a subgroup. You just need that the elements that are in this set to commute pairwise. If that happens for one element in G, then in fact the group G has to be abelian. So saying that, so that shows you that this set solid G can have a lot of control over the structure of G. We also proved that the following were equivalent. That if G were being solvable, each conjugacy class of C, the induced subgraph, is a clique, or that if each of these if the set intersects C for every X in each conjugacy class, that's equivalent to G being solvable. What are you doing for time? I think I've got enough time. Okay, so I want to conclude, I want to return to the commuting graph and look at a different graph related to the commuting graph. So you should note in general, it's not difficult to find non-isomorphic with isomorphic commuting graphs. Remember, in the beginning, I talked about that for simple groups, if you had a group that had the same graph as a commuting graph, it had to be isomorphic. But if you get away from simple groups, it's not difficult to find non-isomorphic with commuting graphs. And in fact, if G1 and G2 are isoclinic and have the same order, then they will have isomorphic commuting graphs. I don't necessarily want to get into what the definition of isoclinic is because it's quite technical, but it's possible to have two groups be isoclinic and not be isomorphic. And so it's known that isoclinism defines an equivalence relation on groups. It does not necessarily preserve order, but if two groups are isomorphic, are isoclinic, so it's sort of a weaker equivalence than isomorphism. Here is, I guess I do give the definition. So two groups are isoclinic if there exists isomorphisms, sigma and tau. Sigma goes from G1 mod the center of G1 to G2 mod the center of G2, and tau goes from G1 prime to G2 prime, and then we need this commutator relation to hold. So we need that the commutator of sigma applied to A, a coset of A, Z of G, with sigma applied to B, Z of G, is equal to tau applied to the commutator of A and B for all A and B in G1. And the fact that the commuting graphs of isoclinic groups with the same order isomorphic was really proved by these two guys, the two gentlemen. And I define C star G to be the graph by taking the commuting graph induced by the transversal of Z of G in G. And the transversal is you take for each coset, you take an element, a representative for each coset of Z of G in G. And it's not difficult to see that the graph that you get is independent of the transversal, since A and B will commute if and only if A times Z1 and B times Z2 commute for all Z1 and Z2 in the center of G. And it's immediate to see that if G1 and G2 have isomorphic commuting graphs, then C star of G1 will be isomorphic to C star of G2. And conversely, if C star of G1 is isomorphic to C star of G2, and G1 and G2 have the same order, then G1 and G2 will have isomorphic commuting graphs. And when G1 and G2 are isoclinic and alpha is the associated isomorphism, from G mod the center, G1 mod the center to G2 mod the center. Then alpha will map the transversal from the center of G1 in G1 to the center of G2 in G2. And the commutator will condition will imply that the pair of cosets in G1 commute exactly when the corresponding pair of cosets in G2 commute. And so if G1 and G2 are isoclinic, then C star of G1 will be isomorphic to C star of G2. And so we see that if G1 and G2 are isoclinic with the same order, then G1 and G2 have isomorphic commuting graphs. And so it makes sense to ask the following. Suppose G1 and G2 are isomorphic with the same order that have isomorphic commuting graphs. Must G1 and G2 be isoclinic? My guess is probably not, but I don't know of any counterexamples. So I would be interested to see a counterexample. Finally, I want to introduce a related graph. So I'm going to define Z of A to be the center of the centralizer in G of A for every element in G out at the center. I'm going to define C of G to be the set of centralizers and Z of G to be the set of centers of these elements. Two facts relate these sets. So we have a bijection between these sets. And the point is that if A is in the centralizer of B, then the center of A is in the centralizer of B, and the center of A is in the centralizer of B, if and only if the center of B is in the centralizer of A. And so it makes sense to define a graph with the vertices in the center of G, and there'll be an edge between Z1 and Z2 whenever Z2 is in the centralizer of Z1. And from lemma 31, we have, Z2 being in the centralizer of Z1, the same as Z1 being in the centralizer of Z2. So it makes sense to think of this as an undirected graph. And basically, I'm going to quickly go through this since I'm out of time, but this shows that this graph really can be obtained as a quotient of the commuting graph. So this graph can be obtained in the commuting graph under an equivalence relation. And so this really gives us another way of generating or gives us another way of thinking about the equivalent to the commuting graph. Okay. All right. And then I'm out of time, so I'm going to skip over this and go to the end. Thank you. Any questions? And let me stop here. Thank you very much.
Thank you, Professor Luis, for your wonderful talk. Let me have some questions if our participants have. Yeah, please ask your questions if you have any.
They are in the chat box.
Okay. There are certain questions in the chat box.
Can we use the average character degree for a character degree graph? Not as far as I know. I mean, it probably, I mean, for the character degree graphs I know of, no, but I mean, I hesitate to say that you can't create a graph using that. There certainly are a bunch of different ways of creating graphs, and people are coming up with, in the last 6 months, I've seen about 5 different new ways of creating graphs with groups. So I wouldn't at all be surprised if there's a way to do it. But I don't know of any right now of using average character degrees for creating character degree graphs. Is there a graph that associates groups with its automorphism and interautomorphism? Again, I don't. So this is Professor Duda's. Duda. How's that? I don't know how that.
Datta.
And I don't. I mean, that would be one I would think it wouldn't be hard to do, but I don't know. I don't know of one off the top of my head. But I mean, you could just replace the group by the automorphism group. I would think that a lot of these constructions should work using the automorphism group in the place of the group. Then a lot of these questions, I think you would be able to would be interesting in that context. So I mean, I think there's a lot of questions that could be asked in that context. There's probably a lot of low-hanging fruit there that could be interesting to be studied. I want to know what we know about a graph by studying characters or faithful characters in particular. I mean, that's a different talk of mine. I do have a paper. I have an expository paper about character degree graphs, and I mean, there is a lot that you can talk about. I mean, there's a number of different graphs that you can create using characters. And I mean, a lot of information you can get from that. The graphs I'm talking about here today are not. I don't have a direct relation to characters, but there certainly are other graphs from Professor Udeep that I could connect you with there. So for Professor Sharma, tidy group. So a tidy group, as I said, for a tidy group, we look at the set cyclic of X. So that's the set of, so for each X, those are the Y's such that the subgroup generated by X and Y are cyclic. A group is a tidy group if that set is a subgroup for every X and G. So in general, that set is not a subgroup. But for a tidy group, we assume that set is a subgroup. Do the commuting graph of a tidy group commuting graph of a tidy group complete? No, not necessarily. Commuting graphs of tidy groups are restricted. I mean, they're a bit nicer than for all groups, but basically, the only way to get a complete graph is to have the group to have each of the connected components being a billion, I believe. Did that answer the question? Okay. And then okay, if we're given a commuting graph of a group, then can we say about the order of its elements of G minus the center of G? Interesting question. I need to think about that. I don't know. Right off the top of my head, I don't know that we could, but I would not be surprised if one could get some information about the order of the elements. So you probably can, because you should be able to look at like the clique of things that all have the same set of neighbors, and that should be give you, because the things with the same set of neighbors are all going to be in the same subgroup, same cyclic subgroup. My guess is that you probably can get. You may not be able to get the orders exactly, but you should be able to get um, some bounds, some ranges on the orders of the elements you from the cyclic graph. I think that, but I don't know that's not that something that's been studied as far as I know. But I mean, I think that's something that you could do that. Um, my the clock my father gave me plays music on the hour. Okay. For the character degree graph, is there any average degree exists? If you were to, it would, again, that would depend on which graph you were looking at. And if you were to label the graph, you could probably come up with an average. The graph that I tend to look at tend to have the vertices as the primes. And in that graph, you would not really have an average. But I mean, if you were to look at the vertices as like the elements and you were to label it with like the orders of the elements, you could probably come up with an average there. Can we think of a way defining a graph in such a way that all the graphs you discuss are the subgraph of that graph? The other than the one at the very end, I don't the where the where I was looking at the ones on the centralizers, no, but the solvable groups, the solvable groups, the soluble graph, the cyclic graph, and the commuting graph, yes. If you take G to be the set of vertices, then yes, you could arrange these so that these were all subgraphs of them. Yeah. Okay. Did my answer make sense? Yes, no?
Yes, sir.
Yes, sir. Thank you.
Thank you, Professor Luis, for your wonderful talk.
Any other questions?
Mona sir, would you like to add some comments?
Say that again?
No, it was a very nice talk, very informative. I don't have any comment. Thank you very much, Professor Lee, for this nice talk.
Thank you.
Thank you, Professor Luis, for your wonderful talk. So here we would like to end the first plenary session of our conference. Thank you all.
Shall we start our second talk? Ma'am?
Yes, thank you, sir.
Nice
Bye.
talk.
Good night.
Good night. Nita ma'am, shall we start our second talk?
Yes, sir, I'm ready.
Okay.
I'm ready.
Okay, so distinguished participant, let us welcome our second talk by Professor Nita Aisha, who is the HOD of the Department of Mathematics, Gujarat University, India. She received her PhD in statistics from Gujarat University in 1994 and a postdoctoral visiting research fellow of the University of New Brunswick, Canada. And her research interests include inventory modeling in the supply chain, robotic modeling, mathematical modeling of infectious disease, image processing, dynamical systems and its applications, etc. She has published 24 books comprising of monographs, textbooks, edited books, and 475 plus peer-reviewed research papers. Her papers are published in high-impact journals of Elsevier, Indus Science, Springer, and Taylor and Francis. She has authored till now 14 books, and many books are yet to come, yet to publish. So, according to the Google Scholar, the total number of citations is over 3600, and maximum number of citations for a single paper is over 196. The H index is 26 up to March 2022, and I-10 index is 94. She has guided 33 PhD students and 15 MPhil students till now. 8 students are pursuing research for their PhD degree. She has traveled to the United Nations, Singapore, Canada, South Africa, Malaysia, and Indonesia to give talks. And she is the council member of Indian Mathematical Society. And today she will deliver a talk with the title Fractional Order Model for Diabetes, COVID-19 Fatality and Optimal Control on it. So with this, I welcome to Professor Shah to deliver his keynote address. Over to you, ma'am.
Thank you, sir, for inviting me to have views on comorbidity. First, let me share the screen. Can you see it, sir?
Yes.
Okay. So thank you once again, because it is only because of pandemic COVID-19 I am visiting the university in 2 consecutive years. And as you said, the title of my talk is Fractional Order Model for Diabetes, COVID-19 Fatality and Optimal Control on it. We all know that India is having a huge number of 27% diabetic patients. And that may be because of our lifestyle, food style, and its lack of exercise and all. And that has increased to 29% during this pandemic because we were all locked at home. No doubt we were working, but we were working on laptop without exercises. And this particular scenario of diabetes and in this talk, I want to have comorbidity of diabetes and COVID-19. It has been observed in eastern states of India. The ongoing pandemic, COVID-19, caused by coronavirus is a single-stranded RNA virus affecting humans, which causes various respiratory disorders because it targets lungs, and then it moves to other parts of the nervous system. Then this high degree of comorbidity with COVID-19 is of great societal concern. What I mean by comorbidity, if a person is suffering from either hypertension or diabetes or cancer or such diseases. And here we are concerning with diabetes. So many diabetic patients are at a greater risk of developing symptoms of COVID-19 because of diabetes. In fact, individual has very low immunity, and so they are more prone to have a COVID-19 infection. The severity has been reported to be highly prevalent in diabetic patients. This scenario is observed in Gujarat, Maharashtra, and Kerala. And it has affected almost 500 million people. This is according to WHO, among which 79% live in a low and middle income countries. So we come in the second category, middle income countries. Control of infectious disease is obviously most important because we had seen it in last 2 years. We are fighting for it, okay, to stop the spread of the disease in the society. No doubt we are under control, but yesterday's media news says that China once again is having a new variant and some part of the China has been locked down. So we need to be careful about once again. Even though due to lack of adequate policies, disease becomes endemic, but still it can be controlled. And that's what we have observed. Not only endemic, we can also control pandemic. Case of SARS in 2010 and pandemic in 2019, or you can say 2020. And for this, we have developed to control we have developed a theory which can control the spread and optimal conditions are obtained to minimize or maximize the objective function. Here by means of optimal conditions, because this outbreak is not a continuous one. It is not going to persist for a number of years. So the solution which we get through the data simulation will turn out to be the optimal, or you will have to assume that it is their optimal solution. Okay, so these are the conditions required. And for that, we have optimal control theory, which is widely used in the mathematical modeling of diseases. And particularly this optimal control theory is part of many of the engineering disciplines. And that since long, to my knowledge, since last 5 decades, we are implementing different versions of optimal control theory in modeling of diseases and to control it. And nowadays, since last 2 decades, fractional order modeling has played a vital role, and it is well known for the memory effect which the integer order model lacks. That is why we need to go for fractional order instead of integer order, because generally we say dy by dx. We never say d half by dx half. Okay. But if you use fractional order, then you can save, it has a property of memory saving. And we get a better result as compared to the integer ordering models. Barrows studied the importance of memory effect of fractional order of COVID-19 pandemic recently, that is 2021. And in his paper, he argued that the variation of COVID-19 in 4 countries, India, Brazil, Italy, and US. This were the 4 countries which he targeted for, and prove that the fractional order model provides more satisfactory result as compared to integer order model. And we will also see in our model in the simulation part. And obviously this encouraged us to apply this fractional order to comorbidity of diabetes and COVID-19 co-infection. We apply fractional order derivative in the Capiccio sense. There are a good number of fractional order derivatives are defined, but the most effective tool, or you can say efficient one, is Capiccio derivative. Because it has the property that the derivative is constant, derivative of constant is null. Okay. Here, if you just recollect in integer order, we say that if derivative is 0, then function is going to be constant. But in Capiccio sense, that is slightly deviated, that the derivative of constant is null. Null will not be considered as a 0. Okay, it is negligible. So to have the fractional order mathematical model, our concentration was on severity caused by the diabetes and COVID-19 infection in the society. That is how much severity, what is the intensity of this co-infection in the society. And also to reduce the spread of either disease, we added even some 11 controls in our model. Now, when you talk about severity for diabetes patient, it is quite normal because diabetic patient has to either they can have medication in the terms of insulin injection. So every time you are passing the needle and you are prone to have the infection. If diabetes is in the advanced stage, in the sense individual has to go for the blood transfusion, or they have to go for cleaning up the kidney periodically. Okay, then this COVID-19 infection is likely to get catch by this diabetic patient, and that is why we say severity caused due to diabetes and COVID-19 infection. Another form of severity you can think of, because the COVID-19 patients are after 7 days was kept on the kept on the medication, which is increasing sugar level. Okay. So there has to be a balance between the sugar level of the diabetic patient and the medication dose. Okay. So the severity is creating a huge problem in case of diabetes. Okay, now let us have a model. We have a susceptible group, individual infected with diabetes or COVID-19. Then you have a co-infection that is infected with diabetes and COVID-19. Then critical diabetes, critical COVID, that means their oxygen level is oxygen, or they have to be kept on ICU. Okay. And once, as I said, severity we need to take care of. That is what the theme of the paper says. So critical in terms of disease, diabetes and COVID infection. So what is the fatality rate? Fatality in the sense death, and not necessary that everybody is going to die, but they can also recover if that immunity is maintained with some natural medications. Okay. So, and this all, so this are the what we call in mathematical modeling of infectious disease as compartments or rooms. All these rooms are connected with certain rates. So I'm just pushing up. These are the rates. Now the last part which has come as mu, that is, it is not necessary that every diabetic infected person will have co-infection through COVID-19. They can survive also. So this mu are natural escape rate from any of the room. But it, so you can see that they are moving from one room to another room. For example, susceptible individuals either have infected diabetic or infected COVID patient. So there is a rate of change, okay, in each room. So I can say what is the rate of change of susceptible or rate of change of infected through diabetes and so on. When you say rate of change, obviously they can be represented by the differential equation. And our theme is on fractional order, Capiccio fractional order. So we have a differential equation which represents the rate of change in terms of fractional order, Capiccio rate of change, I can say, for each room. Okay. Now here some terms are getting positive, some terms are negative. So you can interpret that if somebody is entering in the room, it is taken as positive, and the group or individuals which are moving away from the room are taken as negative. Okay. So I'm just defining what is the COVID critical diabetic, COVID critical comorbidity, fatality, and remove. So these are the differential equations what we have. because from the transmit schematic diagram, I can have this differential equations. And as I said, this D alpha, C D alpha denotes capital derivative with order of derivative alpha. And obviously, it lies between open, close, 0, 1. If it is exactly equal to 1, then you are with classical theory. And if it lies between, it cannot be 0, because I already said it is when you take alpha to be 0, capriccio derivative is null. Okay, that is empty. So it alpha lies between 0 and 1. Okay, now once we have a system of differential equation, then the next thing is when this disease will turn out to be neutral. Neutral in the sense will die out. And for that, I need to get the equilibrium points. So here we have 2 equilibrium points. These equilibrium points are obtained with equating all rate of change equal to 0. So first equilibrium point is COVID-19 free, because we started with those individuals who are suffering from diabetes, and we wanted to visualize what is the rate or what is the chance that diabetic patient will be catching COVID-19. So obviously, when you say COVID-19 equilibrium free point means diabetic patients are there. Okay? And as I said, those individuals who are suffering from diabetes are more prone to have catch of COVID-19. So we have next point as endemic. That is, in each and every room, some optimum number of individuals will be sitting. Okay. Now, how to say that whether this disease will die out when even if person is suffering from diabetes, that is, they will be free of COVID-19. And for that, we have a basic reproduction number, which is technically the number of secondary infections due to a single infected individual in a completely susceptible population. In simple sense, what I can say, if a person is diabetic and suffering from COVID-19, how many more will get COVID-19 if he or she comes in contact with the infected person? Okay? And obviously, we need to have a society free of COVID-19. So reproduction number for the COVID-19 free equilibrium point, which I said here, that is the first point, okay, is calculated using next generation matrix. Some calculation is to be worked out. And what I meant by the reproduction number for COVID-19 free equilibrium point, that means non-existence of comorbidity in society. Okay? And it is given by this R0. R0 stands for reproduction number. Now to have the main theme of the title, that is the fractional order optimal control. What we do here, we put certain controls among COVID-19 to control the spread of COVID-19 among diabetics and vice versa. Okay, that is if you suffer from COVID-19, are you going to suffer from diabetes? And answer is partially yes, but even that diabetes will go away once your medication will getting wiped out. Okay, that is, it goes away. So don't worry, even if you, after getting COVID-19 infection, if you get positively tested for diabetes, it will go away. Diabetes will not stay with you. And that is because of steroid, which is given to control the infection of COVID-19. That is to reduce the infectivity of the COVID-19 in the patient. Some steroids are given, which increases the sugar level of any person, even a person who is not having diabetes. And so what I say, that if you get detected diabetic positive, it will go away. Okay. Now, what are the controls we will have to impose on the model? That is, first thing is the U1 control that prevents COVID-19 infection among diabetic patients by isolating. Slightly not the courageous one, because for how much time? It's already 2 years. For how much time you can stop diabetic individuals to go in a social gathering? Okay, because if you keep a person in a isolation, they suffer from other disease also, and that is what we had observed, because nowadays psychiatric is fighting against such people who were kept in isolation for a longer time. Even our students are suffering because we kept them at home, and now they also have some psychological problems. U2 is the control to avoid diabetic among COVID-19 infectives by providing antibiotics treatment. That is what I said, particularly steroid. U3 is the control to prevent a situation of critical diabetes among diabetic by giving insulin. That is, give insulin in a proper and timely manner to the diabetic patients, so they don't turn out to be the critical diabetic patients. That is, that stage doesn't go to the next advanced stage. Okay, that is what U3 is. Okay. U4 is the control to prevent the co-infection or COVID-19 among critical diabetic. Okay. I said we have 11 controls. U5 is control to prevent a situation of the critical co-infection among co-infectivities. That is, as early as possible, they should be kept on medication of controlling diabetes and COVID-19 both. U6 is the control to avoid a situation of critical COVID-19 among COVID-19 infectives by taking extensive care of ICU patients. So this is only pertaining to those who are suffering from COVID-19, so that it doesn't become critical one. U7 is the control to increase the recovery of critical COVID-19 infective. That is do timely medication so that critical COVID-19 infection can be reduced. Then U8 to U11 are the controls to reduce the fatality rate for the components or compartments, which that is the individuals who are either critically diabetic, co-infected, critically co-infected, or critically COVID-19. And if you look at all these controls, some of the controls are to be maximized and some of the controls are to be minimized. So we need to have a payoff between max mean objective function. Okay. Now, as I said, we need to have a max mean objective function. So I'm constructing this objective function where Wi's are the weights on the compartment, and Ui's are the controls to be optimized, and Vi's are again weights. Now here weight means obviously we will, because now disease is under control, that is under endemic stage, we will keep these weights to be in the range 0 to 1. Obviously open 0, close 1. Okay. Next, define Hamiltonian for the optimal control with the Lagrange's multiplier. And now this Lagrange's multiplier are in general, that is in control theory, are termed as adjoint variables. And to have this adjoint variables, we will use contingent maximum principle for fractional order, which was given by Agarwal in 2010. Okay. So in fact, we are using application of control theory given by contingent in 1986 on fractional order given by Agrawal in 2010. So we have with certain huge calculations, we have optimality conditions for the controls, what we said U1, U2 up to U11, and these are the optimum values of all the 11 controls. Okay. Now, numerical simulation, and for numerical simulation, we have taken data from the either Indian government website, and some of the calculations are, rates are worked out through WHO data. Okay. But this is particularly only for India. Now this says 3D plot we have, that is having a relation between susceptible, infected diabetes and infected COVID-19. If you look at the arrows, see, susceptible people are going towards infected diabetes. That is, they may get diabetes. Okay. In the beginning part, those who are COVID-19 infected are getting diabetes, okay, which very well reflects the real life situation. That is what I said, because infected COVID-19 are kept on steroid, and steroid increases sugar level. Okay. And if you look at the third axis, that is Z-axis, infected COVID-19 is going towards infected diabetes. And that is what this argument says. Okay. Now, here we have a QR for infected diabetes, co-infection, and fatality. Very alarming scenario it is. That is, individuals infected with diabetes gets co-infection and are moving towards fatality class. That fatality class in the sense, very worst scenario, okay, or even can say alarming also. And this indicates that the severity of co-infection, which leads to the increase in fatality, is to be controlled at a larger stage or reduced. Because similar to previous one, here infected COVID-19 were getting removed and they were sitting in the class of infected diabetes. But when the scenario comes that of the co-infection, okay, individual is already having diabetes and catches COVID-19, that means fatality is more, okay, and difficult to even the control. Okay, now here we have infected COVID-19, co-infection, and fatality. Now, if you look at the arrows, it is going away. Okay? So, the moment the population among COVID-19 infected class leading to co-infection, which simultaneously increases fatality in the population, and which may be the case in Maharashtra, Kerala, and Karnataka. I said maybe because we could not find out the data which was differentiating between fatality due to diabetes and COVID-19. We tried our best, but we could not get the data. Okay, but if you had seen the data, or if you had heard from the media, till today, Kerala, Karnataka, Maharashtra is having a huge fatality rate, including Gujarat, but not the one which we had in Maharashtra, Karnataka, and Kerala. Fatality rate was huge. Even it was controlled in Delhi. So that proves that diabetes is not at the alarming stage in Delhi, but maybe in alarming stage in Gujarat, Maharashtra, Karnataka, and Kerala. Okay. Now to find out what will be the criticality, or I can say severity of COVID-19 in diabetic patients. See here, I already saw you formula. And using the data required in the rates, we got R0 is equal to 5. That is one infected diabetic COVID-19 patient was infecting 5 more. Okay. So here, if you look at the diagram, it says that we have 2-period solution. That means it was getting increase in this double way. Okay. But when R0 is 6.2, obviously intensity has increased, severity of COVID-19 is increased among diabetic. So you go up to 6.3, particularly second wave of COVID-19. Then it increased to 6.3. Then one person was giving disease or gifting disease, I can say, to 6.3 more. Okay. And that is 4 times. So 6.3 into 4, that means it is almost 25. That is one infected person was making 25 more infected people. And when it is 6.66, that is reproduction number turned out to be 6.66, it becomes chaos, particularly for diabetic patients. So when R0 is greater than 6.66, there will be chaos in the society with COVID-19 infectives. When I say chaos in the society, means only we are considering diabetic patients. Okay. Okay. Now here, I should also explain why alpha, that is fractional order, is playing a role. Okay. Because in the beginning we said we have a representation of alpha to be memory saving. Okay. So when memory increases from 1 to 0.7, in fact, I should say 0.7 to 1, then the susceptible population decreases greatly when all the 11 controls are applied as compared to the case of the integer model. Because when you take, actually I should say 1 to 0.7 to 1, but purposely I said 1 to 0.7 because when you have memory as 100%, then what is the scenario, which is classical optimization of the control theory? And when memory is only 70%, okay, then what is the scenario for the controls? And here we took alpha is equal to 0.7, that is 70% of the memory was used, 90% was used, 80% was used, and 100% was used. Now in the second figure, when we apply control, the infected diabetic population decreases as compared to those when no control is applied. Here, all magenta color is for without control, and I should say dotted lines are for without control, and solid line is for with control. So if you look at this, any of the solid line and dotted line, for example, alpha is equal to 0.8, okay, then you can see that your disease is under control. Okay. Infected diabetic population is decreasing at a higher rate. Then we have left side, COVID-19 infectives are more when no control is applied. That is obviously dotted line. And when control is applied, it is a solid line. You can see that control is playing a vital role to control, to reduce the infection of COVID-19. Similarly, on the right side, we have the effect of no control and control on the co-infected population. And you can see that it is not exactly the way it should be, but still, I said the way it should be in the sense that something is increasing, decreasing, that is, it doesn't remain uniform. Okay? So we say that it has been observed that in case of control, what is dotted line, the co-infectives are more. And that is what we wanted to control. And that is here. What we have similar result indicating the importance of applying control to decrease critical diabetic patients. So this decrease diabetic patient, critical decrease diabetic patients are those patients who are supposed to have dialysis, but if they can get it pending dialysis and delay the dialysis period, then they are at a better scenario. Here we have the decrease in critical COVID-19 infective when controls are applied. Be careful, dotted lines stands for with control and solid line for with control. Okay. Here in this both the figures, we wanted to confirm about the co-infection and fatality. And on the right side, you can say, because the right side is fatality, you can see that when control is applied, any of the control, okay, then fatality decreases as compared to co-infection, okay? Critical co-infection, one can say. And when we apply all the controls, then recovery rate is obviously going to increase because it is under the control. Okay? And this is for all the compartmental models where alpha range between 0.7 to 1. And here you can see that for alpha equal to 1 is much less compared to alpha equal to 0.7. Alpha equal to 0.7 is on the top, and that is if 70% memory is used in solving the differential equation, then it gives better solution as compared to using 100% memory. Here we have plotted all the controls, and what it says that, for example, in the susceptible class, as I said, diabetic patients, in the beginning, 90% control is required. Okay? And 67% control is required on the infected diabetic patient. Okay. So it is observed that the maximum level of control one should apply to reduce the infection, which will help to reduce the fatalities. Okay, U11, that is the dotted line going on the top, is the reduction in the fatality rate. And it also says that approximately after 5 weeks, all control tend to decrease as recovery rate control for U7 is at its peak. That is, if recovery rate or recovery control is applied to its utmost, that is even that is not required to the huge amount. Okay, it is only up to 52%. Okay, if I apply 52% control on recovery, that is proper medication, then after 5 weeks, diabetic group of individuals are in a better stage. This is when alpha equal to 7, it says that a maximum level of control one should apply to reduce the infection, which will obviously reduce the fatality. And that also says approximately 5 weeks. Okay, because at the beginning, at the 5 weeks, either nearby, okay, peak is up, maximum peak is obtained. Okay, and then they start decreasing, and recovery rate U7 is at its maximum. And when you compare it with the classical one, then we see that previous knowledge helps individuals to take precautionary measures at an early stage. So when memory is decreased from alpha equal to 1, maximum level of controls applied also decreases, and hence it also gives the or emphasize on the importance of memory effect in reaching out to the dynamics of diabetes, COVID-19 co-infection. Now, when U1, U2, and U4 are the controls to decrease co-infection in the population are applied particularly on the infected diabetic class, critical diabetic class, and COVID-19, then we see that these three controls, when applied, we find decrease as compared to the one when there was no control. Okay. Here we have alpha equal to 1 and alpha equal to 0.7. Okay. And even when you increase memory from 0.7 to 1, time duration, time in the sense compilation time also decreases. Here, this illustrates the effect of control U5 and U6 on critical co-infection class. For example, U5, when it is applied to co-infectives, it decreases critical co-infective class. And that means effectiveness of U6 can be decreased. So control applied to COVID-19 infectives will decrease critical co-infectives. That is, at right time, if this control is applied, medication is applied to infected COVID-19, then criticality or severity may be decreased. So as a whole, Capiccio fractional order model for co-infection and basic reproduction number 2.368, which means that a single diabetic person will infect at least two more individuals. These two more are only diabetic. Okay, be careful. We are only focusing on diabetic patients. And the main focus of this research was to reduce the fatalities due to diabetes and COVID-19 under co-infection by applying various controls. We have observed that when controls are applied, then infectious classes like critical diabetes, infected COVID-19, co-infected, that means almost all classes are at a better stage as compared to no control. And simulation also showed the memory plays a vital role in studying the biological dynamics of disease. The plot of the maximum level of controls required showed that with the decrease in the memory from decrease in the memory tends to 1, then fewer controls can be useful. And this suggests that studying the fractional order model is much more suitable, or you can say reliable, when analytic solutions are not possible, and also when integer order level is compared. Controls leading to a reduction in fatality played a vital role when alpha is equal to 0.7. Fatality decreases by 91.45% as compared to integer order class. Okay. So this is what I wanted to say, that one can use fractional order model and control theory on fractional order for here. The thrust area was diabetes and COVID-19. I'm done, and questions are welcome.
So any question from the participant? You may ask in the chat box, or you can unmute yourself to ask directly to the speaker.
Professor Shah, I have a question.
Yes, sir. Good morning. Good morning. Nice to see you.
Also, so in your talk, you have mentioned the fractional. You have mentioned the fractional derivative for the modeling of the problem. So for the different values of alpha, the model would be different. So what are the advantages here in this modeling?
Sir, particularly when such pandemics or such real-time modeling is to be done, we get, for different values of alpha, we get different solution. But it is ICMR, our health department is to decide whether this solution can be taken as a suboptimal or not. It will not be optimal solution. That I can say.
Yeah. Okay.
Another question, ma'am, like in which software you have used to generate the graphs?
I have used different softwares, MATLAB, Maxima, and Maple.
Any other question?
Is there any research methodology or any method of the mathematical model used or not?
Jaideep, I don't get your question. Yes, Jaideep?
Is
What
there
you
any
mean?
research methodology or any method that is used to model this kind of
Mathematical tool, that is a system of differential equation. And then it follows Capiccio fractional order differential equation is used as a mathematical tool.
Yes. Thank you.
Okay.
So thank you once again, ma'am. I hope that this discussion definitely give some ideas to the new researcher in their research direction. And with this, at last, we thank you for your kind presentation. And we hope that we will again meet you in the bilateral session, and you can enjoy our sessions to be present over here.
Till yesterday, Bijoy sir, till yesterday, I was excited that after this, today's lecture, we will meet personally. But yesterday at 8:30, I was just going through the media news and got shocked that once again, variant has come in China.
Oh my God.
And China has already locked down 3 main cities.
So, ma'am, what your mathematical modeling says? Should we cope up with the situation? Or?
Now I will start doing it once again.
So yeah.
Thank you. Thank you for giving me opportunity to share my research.
Yes. One day we can bring all of you to this beautiful campus of Tezpur University, to this historic place Tezpur in Assam. It is very beautiful, and it is very near to the Kaziranga National Park, which is very famous. All of you know about this.
Thank you.
Thank you, ma'am. So next speaker is the very eminent speaker from optimization, and let me introduce with you all Professor Kumar Vuniya, who is currently a professor in the Department of Mathematics, University of Bardhaman, and former associate editor of Obscure Journal, and she had published more than 120 research papers and some very good journals. And his field of research interest includes computational optimization, evolutionary algorithms, interval ranking, and their applications in operation research. So he has more than 25 years of experience in research, and guided so many MPhil and PhD theses, uh, and also a reviewer of many PhD theses from different university, and reviewer of many journals like European Journal of Operation Research, Computer and Operation Research, Journal of Operation Research Society, Computers and Industrial Engineering, and so many applied soft computing also. So he has received so many research projects, and many of them has already completed. So today he will deliver a talk on some important results for nonlinear programming in interval environment. So with this, I welcome Professor Vuniya to address his talk. Over to you, sir.
Yeah. Thank you, Dr. Devnath, for inviting me
It's our
for
pleasure,
this
sir.
conference. Yeah. It is visible. Yeah.
Yes, sir. Yes.
Yeah.
Right.
So, respected and distinguished plenaries and invited speakers, respected members of the organizing committee, dear participants, ladies and gentlemen. First of all, I would like to convey my sincere thanks to the organizing committee, especially to Dr. Devnath for inviting me for this international conference on emerging trends in pure and applied mathematics. The title of my talk is Some Important Results for Nonlinear Programming in Interval Environment. In this talk, I shall try to discuss about the local and global optimality, necessary and sufficient conditions for optimality of nonlinear optimization problems with interval valued objective functions. Also, I shall discuss the extended versions of very well-known conditions, namely Urush-Kuntakar conditions, which is very familiar with the name KKT conditions. Then I shall discuss saddle point optimality criteria for nonlinear programming in interval environment. These are the outlines of my talk. The optimality conditions of a constraint nonlinear programming problem with differentiability, especially Urush-Kuntakar conditions, and also without differentiability, that is very well-known optimality criteria, that is Kuntakar and Fritz-Jones optimality criteria, play important roles in the area of nonlinear programming. These familiar results of optimization problems were developed in Krebs environment, that is in deterministic environment. That means all those results are developed considering the deterministic objective function as well as deterministic constant functions. However, due to fluctuation and randomness of different parameters of the decision-making problems, it becomes a very difficult task to the decision makers to derive the optimality conditions of those decision-making problems where parameters are imprecise. Depending upon the nature of different parameters of a real-life optimization problems, those problems can be categorized in different way. It is Krebs optimization problem,
Hello.
stochastic optimization problem, fuzzy optimization problem, and interval optimization problem. In Krebs optimization problem, the objective function as well as all the constraints are deterministic. In this case, the optimality conditions for both the unconstrained and constrained optimization problems are already well established. The optimality conditions with differentiability assumption of constraint optimization problem with inequality constraints are derived by Kuhn and Tucker in the year 1951. Later, it was observed that Purush has already presented these conditions in his master's thesis in the year 1939. After that, these conditions were known as Purush-Kuntakar conditions or KKT conditions. In stochastic optimization problem, parameters involved in both objective function and constraints are considered as random variables which follow the appropriate probability distributions. And then in this area, several researchers, say namely Cole, Stansiu, Minasian, Prikopa, Bridge and Leibniz, Bhasda, and etc. They introduced a number of useful techniques for solving stochastic optimization problems. On the other hand, in fuzzy optimization problem, well, if you know that the objective function or all the constraints or both, which are considered either as fuzzy sets with appropriate membership functions or fuzzy numbers. In this area, the concept of fuzzy in the decision-making problem was introduced by Bellman and Jade. Then Delgado, etc., in 1994 proposed the advancement of fuzzy optimization in their work. Panigrahi, etc., in the year 2008 studied the fuzzy optimization problem using convexity as well as differentiability of fuzzy mapping. In the recent years, Lee, etc., Song and Wu, Bao and Bai made their significant contribution in this area. Alternatively, if the parameters involved in a nonlinear programming problem are in interval form, then the objective function or constraints or both of the corresponding nonlinear optimization problems are interval valued. In this area, Levin studied the concept of nonlinear optimization under interval uncertainty. Who derived the Purush-Kuntakar conditions of an optimization problem with interval valued objective function. In his work, he introduced two different optimization techniques using Ishibuchi and Tanaka's partial interval order relations. However, according to Kormokar and Vuniya, the definitions of interval order relations by Ishibuchi and Tanaka were incomplete. In their work, Kormokar and Vuniya presented the detailed justification of incompleteness of the interval order relations proposed by Ishibuchi and Tanaka, considering a number of examples. In this work, I have used two interval order relations, greater equal max and less equal mean. You have been used for maximization and minimization problems respectively. For the maximization problems, so if we consider two intervals A and B, which are expressed in the lower bound and upper bound form, as also center and radius form, ACAR, and for B it is BLBU, BCBR. Then, according to Vuniya and Samanto, we can say that A greater equal max B implies that AC greater than BC if AC not equal to BC. That means if the centers of both the intervals are not equal, then if the center of A interval is greater than center of B interval, then we can say that A greater max B. Whereas if the centers are equal, in that case, we have to compare their radius, that is AR less than equal to BR. Here, it is assumed that A greater equal max B, and A only greater max B. This is A greater equal to max B and A not equal to B. Actually, two intervals would be equal when their lower and upper bounds are equal. Similarly, for the minimization problems, in the A less equal mean B, in that case, if AC less than BC for non-equal centers of those intervals, and for equal centers, AR less than equal to BR. And A less than mean B implies that A less equal to mean B and A not equal to B. Here, there should be a question. In both cases, when both the centers are equal, AR less than equal to BR, and the second case also AR less than equal to BR. Actually, these two conditions would be same. Actually, radius means the uncertainty of intervals. In both the cases, the less uncertainty interval would be considered to compare both the interval. Next topic is maximizer and minimizer of interval valued function. So here we consider T, which is a subset of Rn, and we consider a set of closed intervals AB. Now, an interval valued function defined on T is defined by f T from I1R, and it is denoted by lower and upper bound forms fx equal to flx, fux, like that way, where fl, fu both are functions from T to R. The interval function f given in lower and upper bound form can also be presented in the center radius form, that is fx equal to fcx, frx, fcx equal to their sum divided by 2 and difference divided by 2 frx. So an interval valued function can be expressed in the form of lower bound, upper bound, and center radius also. A point x star, a member of capital T, is said to be a local minimizer of the interval valued function fx if there exists a delta greater than 0 such that fl x star, fu x star less equal mean flx, fux for all x belongs to an open ball and their intersection with capital T.
Yes, sir. Yes, sir.
B x star delta is an open ball which is centered at x star and radius delta.
Break in between
And here
session.
less equal mean it is the interval order relations for minimization problem.
We have fallen
So
behind,
this type of
then
definitions
can cope up this.
is seen in
See.
the TRIPS case. So here we have considered interval valued
Sir.
function. Similarly, the definition of global minimizer of interval valued function can be defined in a similar way. That is, a point x star is said to be a global minimizer. So if fl x star and fu x star less equal mean fl x, fu x for all x belongs to capital T. In a similar way, we can define the local maximizer and global maximizer of interval valued function. This is the global maximizer of interval valued functions. The next definition, the interval valued function fx defined on capital T is said to be weakly differentiable at x if both lower bound and upper bound, also center valued and radius, are differentiable at x. Then the function is said to be weakly differentiable. The optimality conditions of unconstrained interval optimization problem. So let T a subset of Rn and F be a weakly differentiable interval valued function defined by fx equal to lower bound and center radius form. Also let grad fcx and grad frx be the derivative of fcx and frx. If x star belongs to T, be an optimizer of interval valued function f, then grad fcx star equal to 0 if fcx not equal to constant. And if it is constant, in that case, grad frx star equal to 0. So this is the necessary conditions for optimality of interval valued function. This is the well-known definition of Hessian matrix. So let f is a function from T to R, be a twice differentiable function on T. The Hessian matrix grad to fx of f is defined as n by n matrix of second order partial derivative. So this is represented by this way. Now the sufficient conditions for optimality. So in that case, so first of all, we have defined the function which is expressed in the center radius form and lower bound upper bound form. And this is the necessary conditions: grad fcx star equal to 0, grad frx star equal to 0, for fcx not equal to constant and fcx equal to constant. Then x star is a member of capital T, be a local minimizer of f over T if grad to fcx star is positive definite when fcx not equal to constant. So if fcx not equal to constant, then grad to, that means the Hessian matrix of fcx at the point x equal to x star is positive definite. And when fcx equal to constant, in that case, the Hessian matrix of frx at x equal to x star is positive definite. On the other hand, x star be a local maximizer of f over T if the Hessian matrix of fcx at x equal to x star is negative definite when fcx not equal to constant, and when fcx equal to constant, then the Hessian matrix of frx at x equal to x star is positive definite. So from this result, we can conclude that an interval valued function is maximum or minimum when we have to test the Hessian matrix of their center and also radius. The example, Find the minimizer of the following example. Minimize f of x1, x2 equal to this function. From this function, it is seen that the center value is only 7/2, which is constant, and frx, fr(x1, x2), this is equal to 2 bracket x1 square plus x2 square plus half. Since fc is constant, so to minimize f, we have to minimize the radius of that function. So from the function, it is clear that 0, 0 is the minimizer of 0, 0 is the minimizer. Hence, 0, 0 is the minimizer of f of x1, x2. And the minimum value of f at 0, 0 is 3, 4 interval. In the second example, here the center of the function not equal to constant. So therefore, and it is a function of two variables x1 and x2. The necessary conditions for optimality, we get del fc del x1 equal to 0 and del fc del x2 equal to 0. Then solving those two equations, we get x1 equal to 0 plus minus 1, x2 equal to 0 plus minus 1. Hence the critical points of fc x1 x2 are 0, 0 and plus minus 1 plus minus 1. Clearly, grad 2 fc 0, 0 is positive definite. So 0, 0 is the local minimizer of f of x1 x2. And the minimum value of f of x1 x2 is 0, 2. At plus minus 1, actually here we get 4 points. So in that case, no definite conclusion can be drawn, as the Hessian matrix at those points is neither positive definite or nor negative definite. Next definition. Let fx be an interval valued function defined on a convex set T. The function f is said to be convex over T if f of lambda x1 plus 1 minus lambda x2 less equal mean lambda f of x1 plus 1 minus lambda of x2. For each lambda belongs to 0, 1, and for all x1, x2, be a member of capital T. So this is the definition of convex function. Sorry. And the proposition, let T be a convex subset of Rn and f be an interval valued function given by fx. So if fc and fr are convex, then fx is convex. Now, optimality conditions of constraint optimization problem. Let us consider the constant optimization problem with inequality constraints. Here, we consider the objective function as interval valued, subject to the constraints gix less than equal to 0, I equal to 1 to what m. And in that case, in general form, we can say that gix, it may be interval valued functions or non-interval valued. So here fc and fr be the function from Rn to R, and gi the function from Rn to R or I1R. Let S equal to the set which contains all the feasible points. Also, f and gi be either continuously differentiable function or interval valued weakly continuously differentiable functions defined on S. Definition. A point X star is a member of S is said to be a minimizer of the problem MP1. This problem is known as MP1. If fx star less equal minimum fx for all x belongs to S intersection open ball B x star delta S. Depending upon the nature and form of fx and all gix, 4 different cases may arise. Case 1, when fx and all gix are real valued differentiable functions. In this case, the necessary conditions for optimality have already been derived. These conditions were derived by Kuhn and Tucker in the year 1951. And from that, these conditions were known as Kuhn-Tucker conditions. And after that, Urus also presented the same results. So these are known as the KKT conditions. This is the case 1. Case 2, when fx is interval valued weakly differentiable function and all gix are real valued differentiable function. That means gix are deterministic functions. In this case, the nonlinear constant optimization problem with inequality constraints is as follows. Minimize fx equal to flx, fux or fcx, frx subject to gix less than equal to 0, I equal to 1 to dot dot m. The necessary theorem, the necessary conditions. Let x star be a local minimizer of the problem MP2 at which basic constraint qualifications hold. Then there exist multipliers lambda I equal to 1 to dot dot m such that the following conditions are hold. Grad fc x star plus summation I equal to 1 to m lambda I grad gi x star equal to 0, lambda I gi x star equal to 0, gix less than equal to 0, lambda I greater than equal to 0. These are the necessary conditions. Here proof is not given here, only results are given. So these are the necessary conditions. Basically, these conditions are similar with the deterministic case, but here the gradient is taken on the center of the function. Actually, in that case, the center of the function is assumed as non-constant. That's why for taking the first conditions, here the center of the function is considered. We call these conditions as extended version of KKT conditions. And note 2, if x star be a local minimizer of L, then at this point L equal to, that is the, this is like Lagrange multiplier. So fc x star plus summation I equal to 1 to m lambda I gi x star plus yi square and fr x star. And this can be written in the form fc x star, fr x star. So the last part of the lower value of the interval would be 0. So the sufficient conditions, the next theorem, let x star lambda 1, lambda 2, lambda m satisfy the KKT conditions 5 to 8, and fc, fr, gix be differentiable convex function with fc non-constant. Then x star be the global minimizer of MP2. In that case, it should be noted that this work has been published in an important, very important journal, Elsevier journal, Computers and Industrial Engineering. And in that paper, the proof of all the theorems and details are given. Here, for the talk, I shall show only the results. So that's why sometimes it would be odd to you in some cases. But case 3, when both fx and gix are interval valued functions and weakly differentiable. In this case, the problem can be rewritten as minimize fx equal to, here we denote this other notation, f lower bar x, f upper bar x, subject to the constants gix, glix, and guix less than equal to mean 0, 0. Without loss of generality, we consider that first k numbers of gix have non-zero centers for I equal to 1, 2, dot, dot, k less than equal to m, and remaining m minus k numbers of gix have 0 centers, I equal to k plus 1, k plus 2, dot, dot, m. Then by definition of interval order relations, the given constants can be written like this way. That is gicx less than equal to 0. Here C, GIC, this is the center of this interval, gix, I equal to 1, 2, dot, dot, k, and gjx, gjrx equal to 0, j equal to k plus 1, k plus 2, dot, dot, m. That means GIACX and GIR be the center and radius of GIX. Therefore, in this case, the nonlinear optimization problem can be rewritten as minimize fx equal to this and subject to GICX less than equal to 0, GJRX equal to 0. Now, using case 2, in case 2, all the objective function is interval valued and constraints are deterministic. So in this case, the constraints are expressed in the deterministic form. So we can use that result. So we get the result 12 to 16, same results. This is lambda I gix star equal to 0 and gjrx equal to 0 for equality constants. And this is the inequality constants, and lambda I is the multiplier greater than equal to 0. Case 4, when objective function fx is real valued continuously differentiable function and all gix are interval valued weakly continuously differentiable. In this case, the problem is of the form minimize fx subject to gicx, girx less than equal to mean 0, 0. And in that case, we can reformulate the problem, that is minimize fx subject to this. So in that case, the objective function is deterministic and all the constants are in deterministic form. So we can use the case 1 to obtain the necessary optimality conditions, and we get the results 17, 18, and 19. 20, 21. So these are the necessary conditions. The example to illustrate these results, we shall solve several examples, and the minimizer of the following interval valued minimization problem minimize fx equal to this, subject to deterministic constants. Let g1x equal to x minus 2, g2x equal to minus x, and here fcx equal to 2x square plus x plus 4 by 2, and frx equal to minus x. Clearly, fc, fr, g1, g2 are convex and continuously differentiable function. Then, according to case 2, the necessary optimality conditions for this problem are given by, we can use the case 2, the optimality conditions. So we get the results 23, 24, 25, and 26. And solving these, we get the results, and clearly x star equal to 0, lambda 1 equal to 0, lambda 2 equal to half. We satisfy all the conditions 23 to 26. Thus, x star equal to 0 is the global minimizer of the problem. The next example, fx, here objective function is interval valued and also constraints are interval valued. In that case, first of all, we have calculated fcx, frx, and g1cx, g2cx, like that way. And it is observed that g1cx not equal to constant, g2cx not equal to constant. And clearly all these functions are convex and continuously differentiable functions. So we can use case 3 for finding the necessary optimality conditions, and we get the results 28, 29, 30, and 31. And solving those conditions, we get the result. The next example, find the minimizer of here. Objective function is deterministic, constraints are in interval valued. In this case, also, we get the same type of results, 33, 34, 35, 36, and solving, we get the x1 equal to minus 1, x2 equal to 0, lambda equal to half. So minus 1, 0 with the global minimizer of the problem, 32. Now, I shall discuss the saddle point optimality of an interval nonlinear programming problem. In the previous section, the necessary and sufficient conditions for optimality of unconstant and unconstant interval optimization problem are discussed. Also, the extended versions of KKT conditions for constant interval optimization problem are established, considering all possible cases regarding the types of objective function and constant functions. All of these conditions are derived considering differentiability assumptions. Moreover, the saddle point optimality criteria, which is known as optimality criteria without differentiability, play an important role in the theory of nonlinear programming. So, the study of optimality criteria without differentiability of an interval nonlinear constant optimization problem is an important research topic. Before going to discuss those, first of all, we discuss interval inequality. First of all, we consider 3 different intervals A, B, C, which are the members of IR and which are expressed in the form of lower and upper bound, also center and radius form. So A less equal mean B, less equal mean C, if and only if we get 4 results. When the centers of all intervals are not equal, in that case, if AC less than equal to BC less than equal to CC. When the center of last 2 intervals are equal and first 2 are not, in that case condition would be AC less than equal to BC and BR less than equal to CR. for equals center values of last two intervals, here we have used the comparison regarding their radius values. So third case, if AC equal to BC not equal to CC, in that case AR less than equal to BR and BC less than equal to CC. In AC equal to BC equal to CC, all centers are equal. In that case, those will be compared with their radius values. This is the lemma 1, interval inequality. Interval minimization and saddle point problems. Here we have introduced interval minimization problem, local interval minimization problem, interval saddle point problems like Fritz zone and Kuhn-Tucker saddle point problems respectively. So we have established the relation between the solutions of them. So first of all, we consider the fx and gi. It would be small fx, sorry, this is a mistake. It would be small fx and gix, and this is also small gi, just due to the first letter of this one, we caps. So these are the center and radius form, also lower bound, upper bound form. The interval minimization problem. So small f x star equal to this one, like that. So here, if we consider this function as the capital Fx, no problem. So it is as the definition is separate, so we can use this one also. So instead of capital F, no problem. So this is the interval minimization problem with the interval valued constraints, and we denote this problem as IMP. And local minimization problem, the same way we can define this one, but for all x, which is a member of the open ball intersection capital X. So we can say that f of x star less than equal to mean fx. So interval Fritz zone saddle point problem. Fritz zone saddle point problem. All of you know the Fritz zone saddle point problem in deterministic case. So here it is extended for the interval environment. So find x star, R0 star, R star. Anyway, if exists such that pi of x star, R0 star, R less than equal mean pi x star, R0 star, R star less equal to mean pi x, R0 star, R star. Where pi x, R0, R, this is the function, which is the center. It is expressed in the form of center and radius. So this is equal to R0 fx plus summation rk gkx k equal to 1 to L, like that way. And it can be expressed in the form of center also. So R0 fcx plus k equal to 1 to L, rk gkcx or R0 frx plus k equal to 1 to M rk gkrx, like this way. And interval Kuhn-Tucker saddle point problem, that is the results are psi x star s less equal mean psi x star s star less equal mean psi x star. And in that case, for psi xs, which can be expressed in the form of center and radius form. Theorem. If x star, R0 star, R star be the solution of IFJSP, the interval Fritz zone saddle point problem, and R0 star greater than 0, then x star, R star by R0 star is a solution of IKTSP, interval Kuhn-Tucker saddle point problem. Conversely, if x star, A star be the solution of IKTSP, and X star 1 A star be the solution of IFJSP. So here the result would be the same in the case of deterministic case. So that's why I shall give the proof of this one. Otherwise, it will not be clear to you. But the theorem statement is same as the deterministic case. But the proof of this theorem would be different in case of interval environment. Let X star R0 star R star be the solution of IFJSP. Then we can write pi X star R0 star R less equal mean pi X star R0 star R star less equal mean pi X R0 star R. Using lemma 1 of interval inequality, 4 cases may arise. Case 1, when center of all these are not equal. Case 2, the center of last two are equal. Case 3, center of first two are equal. And case 4, all the centers are equal. So for all these cases, we have proved the result by considering. So this is the case. So in this case, for this case, we can write FC X star R0 star R less than this and less than this. Then we can write down their function, and it is seen that so R0 star, if we divide both sides by R0 star, so we get this result, and from this result we can express this one as phi c. The function phi psi c. And this function is considered for Kuhn-Tucker case. So psi c X star R by R0 star less psi c X star R star by R0 star less this. That is we can psi X star, this is a center. Then we can write psi X star R by R0 star less equal mean psi this less equal mean psi. Oh, it is not psi c, it is a mistake. Only psi. Similarly, case 2, case 3, and case 4 easily can derive. So combining all these cases, first part of the theorem is good. Similarly, if we consider X star A star be a solution of IKTSP, and then we get this inequality, and then using the function in the form of center radius form, so we can write down this, and then we can multiply 1 with fx, and we can write down this is as, we can explain this with the pi x1s in the form. So we get the result, and this completes the proof. Reverse, the interval valued function pi and psi are called interval valued Lagrangian functions for IFJSP and IKTSP respectively. The m-dimensional vectors R bar, U bar are called dual variables for IFJSP and IKTSP respectively. And the second interval inequality for both saddle point problems, IFJSP and IKTSP, these results and are called as CR minimum principle. So from this one, from the first result it is observed that this is the pi X star A0 star A star is like this. So here this is a parameter. So instead of R, we use S like this way. So here for all X this is, and here X star. So we can say that pi X star R S0 star S star be the minimum value of pi function. Similarly, for the second case also, that's why it is known as the CR minimum principle. So in this talk, the well-known KKT conditions for constant optimization problem and optimality conditions for unconstant optimization problem and have been extended for the nonlinear programming problem in interval environment. Also, the saddle point optimality problem where differentially not considered have been established in this area. There are other several results we have already published, but due to lack of time here it is not possible to discuss all these things. Just in the existing literature, these results are available. Otherwise, if you can contact with me, so I can send the publications of this one. And in that case, till now, we did not develop the duality of nonlinear programming in interval in the environment. So for further investigations, anyone can attack those problems in this one. And these results are totally dependent on the interval order relations, which were proposed by Vuniya and Samant. But for other interval order relations, the results may be different. But till now, the several interval order relations were proposed by several researchers. So among those, in one of the paper, we have shown that this interval order relation is the appropriate interval order relations which can rank all the interval numbers easily. So these are the references, and the co-author of this work, authors are Dr. Ali Akbar Sheikh and our joint research scholars, Muhammad Sadiqur Rahman. So thank you. Any questions from the audience?
Thank you, Professor Vuniya. Let's see if any question is there from the audience, from the participant. So one question come like, what are the main difference between interval valued parameters and fuzzy parameters?
Interval valued parameters actually when an imprecise parameter is expressed by the lower bound and upper bound form, it is interval valued parameter. And on the other hand, an imprecise parameter is said to be fuzzy parameter. So in that case, to represent that parameter, a fuzzy set is considered with appropriate membership function, or to represent the parameter, fuzzy numbers are used. So in case of fuzzy numbers, so there are different types of fuzzy numbers. Which type of fuzzy numbers are selected? And in case of fuzzy set, so membership functions would be selected. So membership function may be either linear or non-linear also. So which would be selected. So in case of decision-making problem, we can say that to take the decision, we have to take another decision regarding the selection of appropriate membership function and appropriate fuzzy number. Similarly, this is the drawbacks. Similarly, in the stochastic parameter, in that case, a parameter is considered as a random variable, then its appropriate distribution is to be selected. Actually, these are selected from the past results. So that's why there is in case of decision making problem, we have to take another decision regarding the selection of probability distribution, membership function, or type of fuzzy number. However, there is a drawbacks in interval parameters also. So there will be a question how to select the lower bound and upper bound. Actually, lower bound and upper bound selection is not a difficult task. From the results, past results, easily one can choose the lower bound and upper bound. So this is a very simple case for choosing this one.
So add to your answer, like how to choose this initial guess, like initial set of solution for a decision making problem. Like for a particular problem, we have to choose some initial guess on the solution. So how should we choose?
Actually, in our cases, the objective function would be internal valued, and that's why this type of problem cannot be solved by existing numerical method or gradient-based method. Basically, we have used the subcomputing techniques like particle swarm optimization, genetic algorithm, differential evolution, like that way, and we get the solution which is best bound solution. As you know, these are the population-based methods, and in that case, several solutions are initialized. So in that case, from the conceptions and from our previous experience, we can select the initial value of the decision variables. Initially, we can take the lower value and upper value with a big gap, and then we can decrease this one by this way.
So since you are senior professor, so I must ask you a question. Like nowadays, every eligible journals or any Springer journals also, they ask that like novelty of the topic and selection of the topic, like you should have something new to the topic. So how like we can find or we can search on the existing literature that these are the topics, these are the new topics that we should go with.
Actually, see, in case of research, there are so many existing works available. So from that, always remember that at the end of each research work, for the further investigations, there is a directions for the new researchers. I suggest the new researchers to follow those and think about the topic to find the new results or new outcomes, like that way.
Right.
In this way, one can develop.
Professor Vuniya, I have one question regarding. Recently, I came to know about something called multiset. Like multiset. Multiset means like fuzzy theory. There is a membership function.
Actually, I have not much idea about the fuzzy mathematics and fuzzy set, like that way.
No, in control theory you have used, I have seen that fuzzy logic is used and fuzzy optimization thing is used.
No, I am not using like that way.
Okay, sorry.
But our extended group, that means my supervisor and his group, they are Professor Manoranjan Maiti from Vidyasagar University, a very well-known name in this field. So they are working in that area. They have published much more works in this area. But from that, I'm not interested about fuzzy. From the beginning, Professor Maiti told me to attack the problems in the area of fuzzy. But from the beginning, I told him, no, sir, I shall try to a new area in this one. Basically, I completed my PhD thesis under Professor Maiti in the area of inventory control, modeling of inventory control. And after that, I switched on this area. In the evolutionary algorithm and subcomputing like that way. After that, I switched in the area of optimization in interval environment. That way. So now,
Recently, so many publications are coming up from in this interval.
Yeah. In different areas, in 0-1 programming, in reliability optimization, obviously inventory control, and several area. I have published several research papers, and my research publications not 120. It is more than now 150, like that way.
Yes, sir. Many of them are in Elsevier also.
Most of the high impact paper journals.
Thank you, sir. Thank you for being here and guide us. And in future also, we believe that we will be able to call you physically in this Techco University campus. So, thank you, sir.
Thank you very much. Okay.
Professor Devnath, can we go for the next session?
Yes, please go.
So once again, I would like to welcome to our fourth session, and we have Professor Ritumani Sharma from IIT Delhi with us.
Welcome, sir.
Let me introduce briefly Professor Sharma. Professor Ritumani Sharma did his PhD from TIFR Mumbai in 2004, and soon after he joined Vertices Research Institute as a postdoctoral fellow. After that, he joined the faculty of IIT Guwahati, and then finally he joined IIT Delhi and in 2009, and he's working there since then. Professor Sharma has expertise in group theory, number theory, and their applications in algebraic coding theory. In today's talk, he will discuss about stability of certain higher degree polynomials. Professor Sharma, please.
Okay, thank you. Thank you, Rajat. I would like to thank all the organizers of this conference, and I congratulate all of them for successfully organizing this activity. And I welcome all of you. And I would like to share my screen. Can I?
Yes, sir, please.
Can you see my screen?
Yes, sir. It's coming.
Okay.
Yeah.
Okay, thanks. So I'll be talking on stability of polynomials. And this is a joint work with Himanshu Sharma and Laisram Santa. So mainly we are going to look into iterates of polynomials of the form x to the power d plus 1 upon a non-zero integer c. Before we go into that history and methodology, we need certain preliminaries. Suppose phi is some map from a set S to itself. Then we define its iterate. Nth iterate is composition of the map with n minus 1 iterate, which is here. So an F0 we are going to write for the identity map. So you see this map should be from S to itself. Then only we can do this iteration. And these kind of maps are studied in arithmetic dynamics, and that is kind of motivation for these kind of problems. Given such a map, given a point alpha in S, we apply successively phi on alpha. So alpha, phi alpha like this, phi square alpha, that means we are applying phi on phi alpha. So this set phi n alpha for n bigger than or equal to 0 is called the orbit of alpha under the map phi. A principal goal of dynamics is to classify points of the set S according to the behavior of the orbit. So in this talk, K is a field, and we are going to take some point from the field, and the functions that phi, sorry, this is just phi, not the capital phi, is a rational function. That means it is quotient of two polynomials, coefficients coming from K. We assume always that fz and gz are co-prime. We know that kz is a PID. We can say what is the meaning of co-prime, etc. And degree of a rational function is the maximum of the degrees of the polynomials fz and gz. So these rational functions are required to. And another thing, that given a point, we say that the point alpha is periodic if phi n alpha is alpha for some natural number n. Right? So periodic anyway we need in all branches of mathematics, period and periodicity. So another terminology is pre-periodic. So it may not be periodic, but it may be pre-periodic. So it means that some phi n alpha is periodic. So phi n alpha is equal to phi m alpha for m not equal to n. So then we say that alpha is pre-periodic. And when alpha is pre-periodic, the orbit must be finite. And if orbit is finite, the point alpha must be pre-periodic. And the other extreme is wandering point. A point is alpha is called a wandering point if it is not pre-periodic. That means if the orbit is infinite. So here in this example, z square minus 1 is a pre-periodic point. Suppose if I substitute 1 here, I get 0, and then I substitute 0 here, I get minus 1. So the collection will be 1. This is my alpha. Then after substituting, I get 0. Then after substituting 0, I get minus 1. Then I substitute minus 1 there. Then I get 0. So this now repeats. So you see this 1 is a pre-periodic point, but it is not a periodic point. Whereas 0 and minus 1, these are periodic points. And this 3 is is actually a wandering point for this map. All right. So again, some preliminary concept of discrete valuation. For a field K, a map from K to Z union infinity is called a discrete valuation if it satisfies the following 3 properties. That nu of x is infinity if and only if x is 0. Nu of x times y is sum of nu x and nu y for every xy in K. And nu of x plus y is bigger than or equal to minimum of nu x and nu y. So example, for the field of rational numbers, take any prime p. Then any rational number x can be written as p to the power some t times another rational number x naught. How do I pick x naught? X naught is such that its numerator and denominator are not divisible by p. Then pth valuation of x or p-adic valuation of x is defined to be this t. For example, if my p is 2, then p-adic valuation of 4 is 2, whereas p-adic valuation of 1 by 4 is minus 2. P-adic valuation of 5 is 0. 2 does not divide the numerator and denominator. All right, so I am sure most people have seen this. And given a discrete valuation on a field, one defines an absolute value, which is call a non-Archimedean absolute value by this relation that modulus symbol we use, mod of x, is lambda to the power nu x, where lambda is a fixed positive real number less than 1. Then this non-Archimedean absolute value satisfies these three properties. Namely, absolute value is 0 if and only if x is 0. Absolute value of x times y is product of absolute values of x and y. And absolute value of sum of x and y is less than or equal to maximum of x. Absolute value of x and absolute value of y. So we know Archimedean one satisfies a weaker condition than this. Namely, the triangle inequality kind of thing, but this is stronger. All right. Suppose phi is a rational function, and I write down the iterate of phi. So if phi z equal to z, sorry, phi z equal to say z square, what is phi square z? Phi square z is z square whole square. That means z to the power 4. So this way, if phi z is fz upon gz, we need to find what is phi 2z, phi 3z, and so on. Then phi nz, we write again is a rational function, and we write its we denote its numerator and denominator by fnz and gnz. They are polynomials from kz here, and we always assume that they are co-prime. So definition of stability, that phi comma alpha is called stable if fnz minus alpha times gnz is irreducible over the field K. This condition of stability is too strong. For instance, it is not preserved under finite field extension. There is a weaker condition which is called eventual stability. So what is that? We say that phi comma alpha is eventually stable over the field K if the number of irreducible factors of fnz minus alpha times gnz is bounded by a constant which is independent of n. So this should hold for every n bigger than or equal to 1. Okay, so stable phi minus alpha is stable implies phi minus alpha is eventual stable, because number of irreducible factor in case of when phi comma alpha is stable is just 1. So here we are saying that there should be a bound on the number of irreducible factors of iterates. So if phi comma alpha is eventually stable over K, then it is eventually stable over any finite extension of K. Next, given a discrete valuation nu on the field K, one can look at this ring, subring of K, those elements in K whose valuation is non-negative. And inside this ring, there is a unique maximal ideal which consists of those points in K whose valuation is positive. And therefore, the quotient R upon P is a field, and it is a field of finite characteristic. So given a point in K, or even a point first in say R, we can talk about its quotient by P. So we denote it by x bar. X is in R, then x bar is in small k, the residue field of R. So here, suppose I have a polynomial with coefficients coming from this R. Then we define f tilde. What is that? Every coefficient we go modulo the prime p. Then this is extended for maps coming from K round bracket Z. That means for a rational function which is a quotient of polynomials. So this is the definition. If phi z is fz upon gz, then phi tilde z is f tilde z upon g tilde z. And here in this case, at least one of the coefficient is supposed to be a unit. So the definition of good reduction. A rational function is said to have good reduction at nu, the discrete valuation nu, if degree of phi and degree of phi tilde are equal. So when we go modulo p, many certain coefficients are going to disappear. So as a result, degree may drop. So if degree of phi and phi tilde are equal, that means degree does not drop as a result of going modulo p, then the rational function phi is said to have good reduction at nu. So another concept is rigid divisibility sequence. A sequence in K, say AI, I equal to 1, 2, 3 like this. So sequence means a map from the set of natural numbers to K. So this is called rigid divisibility sequence with respect to some absolute value, which is non-Archimedean. So if it satisfies two conditions, quite interesting, that if an has absolute value less than 1, then absolute value of an and absolute value of akn are equal for every k bigger than or equal to 1. And condition 2, if absolute value of an is less than 1 and absolute value of aj is also less than 1, then absolute value of GCD of n and z is also less than 1. You see, we are applying GCD on the suffix. Here n and j, an and aj have absolute value less than 1, then we are saying a of GCD of n comma j has absolute value less than 1. And combining these two, one can see that if absolute value of an is less than 1 and absolute value of ak is less than 1, then an and ak have equal absolute values. See, when it is a non-Archimedean absolute value, then the property what we write for on reals, that absolute values are equal if and only if they may be equal or they have different signs. Only there is a difference of signs only. That kind of thing is not here, right? So this is with respect to some prime. And there is a theorem, and this is also an example for us, that given a polynomial function phi, not just any, but this theorem is for z to the power d plus c, where degree is at least 2. If 0 is a wandering point for phi, then phi and 0, the iterates of phi evaluated on 0, this is a sequence, and this sequence is a rigid divisibility sequence. Okay, so for example, I can take z square plus 1. So I have to check whether 1 is a wandering point. That's not very difficult to see, right? So if I substitute 1, then I'll get 1 plus 1, 2, 1 comma 2. Then I substitute 2, I get 4 plus 5, and so on. So 1 is a wandering point for z square plus 1. And this theorem says that these values, when I apply phi n on 0, I get a rigid divisibility sequence. So this theorem is helpful in doing certain results of stability. So therefore, we included this result here. So a result here, due to Jones and others, published in 2017, that if phi is a rational function and alpha is a pre-periodic point of alpha, then phi comma alpha is not eventually stable. And the conjecture that converse is true. This is a conjecture. So objective is to see a proof of this. To prove it. So degree 1 case we just remove, because when it is degree 1, then it is stable. It's a routine check. One can just write down. So the first result, that for some non-Archimedean absolute value, if for this polynomial zd plus c, the absolute value of c is less than 1. You see, what you think of k to equal to q. So I'll have c to be what? A rational number whose numerator is different from 0, -1, or 1. So that there is a prime that divides the numerator. Then with respect to that prime, if I write down the absolute value, then the absolute value is less than 1, or the discrete valuation is bigger than 0, right? So that is an example which is easy to see. So then the conclusion is that for this polynomial with this kind of choices of C, phi is eventually stable. And in this one, there is no discussion about number of irreducible factors, however. And this rigid divisibility of this polynomial, which I just stated earlier, is also helpful to improving this result. So this theorem, I have already said, this corollary, that when I am looking into rational numbers, I just need C to be different from a reciprocal of an integer, or it should be non-zero, then phi is eventually stable. So what is remaining? The remaining thing now is that C is the reciprocal of an integer. Then is it eventually stable? Who is eventually stable? Z to the power D plus C is eventually stable. So now on we are going to think of C to be 1 upon some integer. All right. But before going into that, there is a result which takes care of certain cases of Z plus 1 upon C, or 1 upon an integer, where the concept of good reduction is required. So this says that if phi is a rational function of degree at least 2, and it has good reduction at some discrete valuation on K, such that when I go modulo the corresponding prime, then phi tilde should look like this. Okay, so small p is a prime, and the statement is that phi comma alpha is eventually stable if alpha is not a periodic point for under phi. Alpha is not a periodic point under phi. So this now is helpful to conclude certain thing, but before that we also state another thing, another result, which says, I mean, it is in the same direction, but here it talks about the number of irreducible factor of iterates of this. What is it? So we know what is alpha tilde. Alpha tilde is obtained from alpha by going modulo the prime that defines the discrete valuation nu. Discrete valuation nu. So for this alpha tilde, what is the period under phi tilde? So suppose I is the period for alpha tilde under phi tilde. Then the maximum number of irreducible factors of iterates is given by the valuation of phi I alpha minus alpha. Okay, this is that same I, namely the period. And if nu alpha, the valuation of alpha is negative, then this quantity is simply this, the valuation of phi alpha inverse minus alpha inverse. Okay, so this is just for completion I have included. So it may be slightly hard to follow for some people. So I just go quickly this part. So now what I do, I look into nu, which is defined by, for rationals, the discrete valuation defined by 2. That means two-adic valuation. Then if I consider this example, that z square plus 1 upon a is an integer. So I consider a to be odd. Then you see z square plus 1 upon an odd number, it has got good reduction at 2. Because if I go modulo 2, the odd number will not be disturbed. It will not become 0. And degree of this polynomial will remain 2. So phi tilde and phi will have same degree, namely equal to 2. Okay, so therefore the theorem, the previous theorem is applicable to this polynomial, and therefore we can say that this polynomial is eventually stable at 0. That means phi comma 0 is eventually stable. But now what is remaining, that for this polynomial z square plus 1 upon a, where a is an integer, which is an even integer, the theory is not applicable, then what one can do? So this is now remaining. So to prove these results, a lemma is very useful. This lemma, I'm just writing here, stated here. So what does it say? So it says that suppose the field is K is a field of characteristic different from 2. For us, maybe K equal to Q only. So suppose G is a monic irreducible polynomial of some degree, say R. And fx is some monic quadratic. Okay, later we are going to replace quadratic by some other degree. Then it says that look at these numbers that we evaluate f on its critical point. Gamma is a critical point of f. That means gamma is a root of the derivative of f. So we apply f on gamma, then g on it, then multiply it by -1 to the power degree of g. So this number and these iterates g composed with f and gamma for n bigger than equal to 2. So if we can show that these numbers are non-square, each of them is non-square, then the iterates g f n x is irreducible. So irreducibility of polynomial is given by non-squareness of certain an infinite family of elements coming from K, which are defined by using these polynomials G and F. Okay, so that's how it is interesting, but this family is also infinite. But as we know, whether it is non-square, perhaps is a slightly easier question than verifying whether some polynomial is irreducible. So now they prove using this theorem, this lemma, and that for this quadratic polynomial where C, R is 1 upon C, and where C is different from 0 or -1, when C is between -10 to the power 9 to +10 to the power 9 on this range, frx is eventually stable over Q, and the number of irreducible factor is at most 4. So this is a result, and this result of Jones and others is the method we apply for this polynomial x cube plus 1 upon c, where c is an integer, and we have got this one that when c is between -10 to the power 5 to 10 to the power 5, then number of irreducible factors of iterates of frx, which is x cube plus 1 upon c, is at most 2. Okay, and to prove this one needs a lemma which is analogous to lemma which is required to prove theorem 2. So we are calling it lemma 1. So here maybe k equal to q, and f is this cubic polynomial. You see, it has only one critical point, right? Because critical points, cubic are supposed to have two critical points, that they are equal here. That means critical point means 0 of its derivative. And again, G is a monic irreducible polynomial. So the statement is, the conclusion is that this iterates G composite f and z for every n is irreducible if these numbers, this infinite sequence of elements coming from K, namely G, f, and 0, for every n is not a cube. So here I do not have to write -1 to the power r, because we are talking about this is not cube. For square, I had to take care of sign. For cube, I don't have to. So this looks slightly less complicated. But to prove lemma 1 or the lemma which we saw before, one utilizes some lemma which is referred to as Capilis lemma. I just state here. For two polynomials, composition is irreducible if and only if G should be irreducible and fx minus beta is irreducible over k beta, where beta is a root of g. So since g is irreducible, beta cannot be in k. So beta lies in some extension of k. And so this is what. So this lemma is very helpful to prove this lemma 1. And to prove lemma 1, it is by induction. For n equal to 0, we have just gz, which is irreducible by hypothesis. This is our anyway hypothesis. Induction hypothesis is what? The G composition Fn minus 1z is irreducible. Then by Campbell lemma, what we need to show G Fn z is irreducible if z cube plus 1 upon c minus beta is irreducible, because gz is given to be irreducible. So this polynomial, this cubic, is irreducible. That means what? That means 1 upon c minus beta is not a cube in K. Okay. But what is the norm of 1 upon c minus beta? When we compute the norm, so I have to take product of 1 minus c minus conjugate of beta, say alpha. Alpha is a conjugate of beta, and I have to take product over all the conjugates. When I take product, I get G Fn minus 1 upon c, and which is nothing but G Fn 0. So, and when a certain quantity 1 upon c minus beta is, question is about whether this is a cube. If I know that norm is not a cube, then the original quantity, original number is not a cube. So therefore irreducibility, therefore G Fn 0 is not a cube implies norm is not a cube. Therefore 1 upon c minus beta is not a cube, and hence by Capitalist lemma, the iterate, namely G Fn z is irreducible. So that's what we wanted. So this completes the proof of the lemma. Another result in the for cubic is for which we use good reduction theorem. We prove that for when C is 2, 4, 5, 7 modulo 9, then iterates of z cube plus 1 upon c is are all irreducible. And when c is 1 or 8, then number of irreducible factors turns out to be 2. Okay, so and this result is helpful to prove theorem 3. And we recall what is theorem 3. We want to show that x cube plus 1 upon c for on this bound for c have got at most 2 irreducible factors for the iterates. So in this direction, there are two possibilities. X cube plus 1 upon c itself may be irreducible or may be reducible. Suppose it is irreducible. So then by lemma 1, what we need to verify that Fn0 is not a cube. Fn0 is not a cube. That's what you need to verify. But this is an infinite collection, Fn0. For every n, I need to verify this. So what is the trick? Now, trick is, you will observe that Fn0 is not a cube if Fn0 modulo some q, where q is co-prime to c, is not a cube, right? Because if I have a number, say I have an integer, if it is a cube, then if I go modulo any prime, for example, it remains a cube. So if I know when I go modulo some prime, it is not a cube, then the original number cannot be a cube. So this is the argument we are using. So if we are lucky, we may be able to. Another advantage is that when I am going modulo q, how many possible values of Fn0 are there? At most q many, namely 0, 0 bar, 1 bar, 2 bar, like that, q minus 1 bar. So even if I vary n, I'll have at most q many values of Fn0, right? So if we are lucky, then for some number q, in fact, we are using primes. For some prime q, we may be able to show that Fn0, none of the Fn0 is a cube. And in fact, that is the case. We use primes up to 500 to show when C is bounded by 10 to the power 5, that Fn0 is not a cube. Of course, we cannot do it manually. Similarly, when F is a product of two irreducibles, because we may be able to factorize Fz because it is a cube. For example, this is true when C is M cube, and in this case, irreducible factors are this, and we know how to handle this case. Okay, in this case, limit is up to 10 to the power 18, but with Sage is very helpful to do this kind of computation, whether some element is a cube. Okay. Now let us look at finally the case of x to the power d plus 1 upon c. Okay, so here we are going to assume d is bigger than or equal to 4. So for this polynomial, 0 is the only critical point, because if I differentiate, I will have x to the power d minus 1, d into x to the power d minus 1, and 0 is the only critical point. 0 is the only solution. But let us observe that in this case, Fn0 has got this form. So what we are writing, for example, F0 is 1 upon c. Then F20, I'll just substitute x power d by 1 upon c and plus 1 upon c. So more generally, for any n, this equality is true. And another thing we should note is that an and an minus 1, they are related in this fashion. Okay, so these are to be noted, which is a routine check. Another interesting property, important thing, that an minus 1 and c, they are pairwise co-prime. Okay, and a generalization of lemma 1 is required for this polynomial. And you perhaps can guess now what is the generalization. So even here, G is an irreducible polynomial of some degree, say R, and Fz is z to the power d plus 1 upon c. Okay. So maybe I'll just take k to be equal to q. Okay. So because I don't want to look into field of positive characteristic in this case. So therefore, this I'm writing as q or any extension, a finite extension of qc. Then again, using Capilis lemma, we show that these iterates are irreducible if no members of this family is a pth power for every prime dividing d. When d was 2 or 3, I do not have to worry about primes dividing d because the number itself was prime. Now we may have more than one prime dividing d. So we need to verify it for every prime p. Okay, this is how it is different, but however, proof is quite similar, Okay, so now verifying iterates of these are irreducible boils down to show that Fn0 is not a pth power in Q. So because we are restricting ourselves now to Q. And for this, what we need to do, I just go back and show that you see the denominator, you think of this d is divisible by some p, the denominator is already a pth power. So therefore, Fn0 is a pth power if and only if an is a pth power. So numerator is a pth power. So I don't have to worry about denominator. Okay, so I will just look into the numerator. That's what we have written here. So Fn0 is a pth power. If we can show this is not a pth power, so an is not a pth power. So it is enough to show that n is not a pth power. Okay. For this, we need some knowledge from Diophantine equations. So this Diophantine equation, a definition, ABC, this triplet is a solution, and this solution is called proper if they're co-prime, pairwise comprime, and called non-trivial solution if their product A, B, C, this is not equal to 0. And that means none of them is, at least no one is 0. If at least one of them is 0, the product will be 0. And ABC, a solution ABC is said to be a primitive solution if it is non-trivial and proper. Okay, so here is a lemma, maybe actually theorem for us lemma, but here is a collection of Diophantine equations. There are many more Diophantine equations for which there is no primitive solutions, but we are using some of them. So I have just listed a few of them. So this is a theorem now that x bar d plus 1 upon c, where d is bigger than or equal to 4 and c is a non-zero integer, then fx is stable. Stable, that means its iterates are irreducible for the following possibilities of d. So first one says that d is divisible by neither 2 nor 3. So for d equal to 5, say d equal to say 5 times 7, 35, because it's not divisible by 2 or 3. Then it is stable. X power 35 plus, sorry, x power d, x power 35 plus 1 upon c is stable, for example. Case 2, d is some power of 2. Index is at least 2. So 4, 8, like this, 16. Case 3 is d is a power of 3. Index is again at least 2. Lastly, the last condition, that last one case, that d is a power of 6. It is like if the index is at least 1, so that means 6, 36, etc. Okay, so the case 1 was proved long back in 2002 by Danielsons and Fee. So we'll not talk about it. So the proof, to prove the other cases, you recall that here our fz is this, and fnz again, I'm just marking here. You see fn0 looks like this. I need to worry about an, that an is not a p power for a prime p dividing d, and an satisfies this relation. Okay, so now what do I need to check? That an is not a p power for each prime dividing d. But in case 1, our d2 is the only divisor. Okay, and an satisfies this relation. Now I just replace d by 2 to the power m. So now you can see that if an is a square, if an is a square, then there is a primitive solution to this Diophantine equation, which is a contradiction. Okay, this Diophantine equation has no primitive solution. Similarly, for x power d equal to 3 to the power of m, again I have replaced d by 3 to the power m, and I have got this relation. Then what I need to check, that an is not a cube, because I want iterates of f to be irreducible. So n is a cube implies there is a primitive solution to Diophantine equation, again which is a contradiction. Finally, for d equal to 6 or its powers, I have just written the arguments for the 6. N, you can see this one, and n is a square, then this Diophantine equation has got a primitive solution, and n is a cube, then the next this one has got a primitive solution, and which is both are false. None of them is true. So therefore, iterates of f must be irreducible by the lemma. Okay. So so this is what I have just said is written here. But what we have is now that there are infinite possibilities of d, for which it remains open. The question is unsolved. I mean, it is expected, so it is a conjecture but it's not yet proved. Okay, so here is the list of references that we have used. So for Jones paper, the first 2, 3 actually, and this for arithmetic dynamics, one can look into this book of Silverman. And Danielson's paper is here. This is iterates of x to the power n minus b, which is the case 1 for us in the last theorem. Okay, so thank you for your patience. If any questions, please.
Any questions from participants? I have one question.
Yes, please.
Yeah.
Sir.
Just a minute. I have one question regarding the stability of x cube plus 1 by c.
Okay.
So in that case, you have classified the integer c as modulo 9.
Yes.
So why modulo 9 comes in that case?
No, that's what I have said, that reduction, we have to go modulo reduction, I mean good reduction. So 3 is the number. Okay. So but irreducibility we did not get. So when we go modulo 9, we could just list the numbers. See, we go modulo 3 actually here. Okay. And it is a good reduction for when c equal to these numbers. When it is not different from 0, 3 or 6, then it has got good reduction. Okay.
So if I change this 3 by some other, then how can
no, my cube, this is cube, no? So my p is 3. Okay.
Okay.
So maybe I'll go back to some result which is used here. Yes. So now I'm applying it for 3. You see how many factors are there. This factor is given by this number, which is the period of alpha tilde. Okay. So for some number different from 0, 3, and 6, it is the orbit. The period is 1. They are namely what you have said, that when it is 2, 4, or 5, and 7, the orbit, the period is 1. And when it is C or 1 or 8, then orbit is, the period is 2.
So
okay.
Suppose if I want to change here 5, 3 by 5.
Oh, you are saying then I have to go for this 5 here. Okay. That's right. So question is different then.
Then what? Then
so
this
then,
C, yeah.
Yes. Then I'll see that this C should be what? 1, 2, 3, 4. 5 I cannot write. Okay. So what I'll try to do, I'll find it's a good reduction now. So what I'll do, I'll find the orbit. Okay. I'll find the orbit of and then I apply what is the period, and if you are lucky, the suppose period is 1, that means my conclusion will be that it is irreducible.
Okay.
Yeah.
Thank you.
Okay. So
any more questions?
So thank you, Professor Sharma, for such a nice.
Sir.
Firdaus has some question. Firdaus, you had some question? Yeah.
Yes, sir. Actually, I want to know one general thing, that we know that you did your PhD from TFR Mumbai. Okay. So would you like to say a little bit about your journey to TFR? Because since at that time, very few people from our northeastern region know about that prestigious institution.
Okay. So who are you? Can you tell your name, please?
Yeah, I am Vertices from Tezpur University.
So you are doing PhD or?
Yeah, yeah, I am also doing PhD under Dr. Rajat Kalinacha.
Okay, okay. Yeah, well, so I studied in Tezpur actually till my BSc, and then I came to Delhi, and in fact I studied in IIT Delhi. And before I come here, I hardly knew about anything about TIFR.
Hello.
So I was motivated some by one of the professors that why don't you try? You should try basically. You should do well, because he was aware that I have interest in mathematics, not for a job immediately, because at that time people who do MSc from here, many people get a job, in certain companies, software companies, IT companies, and he was aware that I was not interested. So he kind of he encouraged me and a few of us, you should try TIFR, for example, and of course many other places. So, and that's how I know. Not much preparation. I mean, we studied whatever was here, but we applied, and lucky to be there. The luck factor is also there always, and that's what I think. Okay. Yeah. So that's all. So I never thought of going abroad for PhD, and so it was a good kind of option for me at the time that I go there. So of course I tried for IISc also, but at that time I was told that maybe you join TIFR. Have I answered your question? I don't know.
Yes, sir. Thank you, sir, for your comment.
Okay.
It was very encouraging also.
Okay. Yes, sir.
So.
Yeah, and from you only I got the inspiration to go HRI for postdoc.
Oh, really? Okay.
Thank you very much for your wonderful talk.
Okay, and thanks everyone for the patience. And I understand that this kind of abstract mathematics to see for a long time is difficult and sometimes painful. So yeah, I can see Professor Manoj also.
Hi, everyone.
Hi.
Okay, then thank you to all the Professor Shah, Professor Jaggi, Professor Manoj Kumar, Professor Sharma, and all of them, and participant also. And here we conclude our first session. Now, after lunch, we will coming back at 2:30 to hear the talk from Professor Jaggi. Okay, sir.
Thank you all.
Thank you all.